Okay, great. Looks like we are live.
Hello, everyone. Should we start now or wait a few more minutes?
I think we should probably get started because we have a schedule to keep, right? Do you want me to share the evaluation before we get going?
Yes. If you could share the evaluation form and the schedule on the chat, that would be great.
Okay.
Welcome, everyone. Welcome the students and mentors and our YouTube friends. So today we will have 6 talks in the morning and 6 afternoon time about the space physics and solar physics. And so each talk will be 20 minutes. We think of 18 minutes of talk and a few minutes of questions. Please fill up the evaluation form for the student. The schedule is posted on the chat here. So welcome our first presenter, Lauren Williams, from University of Missouri, Columbia. And she already shared the screen. So
yes,
let's start.
Hi, I'm trying to get my cursor to be able to be seen. I can't do it for some reason. I apologize for the technical difficulties. Let me pause the share. Okay. Sorry about that. I have to get my cursor on the screen and I can't see it. So that's really weird. Let's try this again.
Yeah, try again.
Okay. Let me do this now. Okay, can you see my spotlight cursor?
Yes, we can.
Okay.
Oh, we could. Yes, we can.
Okay, I don't know what happened to it. But okay, I'll start. So hi, my name is Lauren Williams, and my project is based around comparisons of novel imaging and spectroscopic infrared eclipse observations in 2017 with my mentors Dan Seaton and Amir Caspi, and with the help of Jenna Samra. So the main research question that was focusing on this summer is, what is the nature of the IR emission from the corona, and what can we learn from it? We're using multiple IR observations to characterize the value of this regime for studying the corona, and there's a possibility that IR observations in the corona can open up new windows for future missions. The total solar eclipse of 2017 was named the Great American Eclipse because it had been almost 100 years since a total solar eclipse spanned the entire United States, and about 38 years since a total solar eclipse was visible anywhere in the States. So this is a really big deal. Eclipses are important because they are the perfect coronagraph, basically. They give us a great opportunity to study the solar corona, which actually extends millions of kilometers into space. And by taking spectroscopic measurements of the plasma properties, we can see strong ionization, and we can see that the plasma temperatures can get up to around 1,000,000 degrees Kelvin, which is much hotter than the surface of the sun. So observing the corona can help us better understand these structures. One of the primary opening questions about the corona is why or how its structures remain so smooth and well organized. They're in the photosphere, where turbulent motions bring twisting and other complexities, and observing these really fast motions can help provide insight into the mechanisms that smooth and comb out the corona. So high speed and sensitive imaging is needed. So now the question is, how can we observe the corona? Observing in space is expensive, and the type of instrumentation is limited, and observing from the ground can be very difficult because the atmosphere absorbs and emits different wavelengths. Airborne observations can get around a lot of limitations I previously mentioned. So our project used 2 of NASA's WB-57 high altitude research aircrafts, which are adapted from old B-57 bombers. And these planes are designed for high altitude, so they can fly up to 65,000 feet, which is beneficial for observations because that gets above about 85 to 90% of the atmospheric air mass, and that helps improve image quality. So not much is known about the corona in midwave infrared, and that was the goal of this mission, to observe and take an image of the solar corona in midwave infrared. And here's an image of the Ares dynamite system, which is the cameras that actually take the observations on the nodes of the aircraft. And it's equipped with a television camera on the right. I'm sorry you can't see my cursor. And then a midwave infrared camera on the left. And here, this is a clip of the system on the nose cone, and it's able to move independent of the airplane. So it can track the eclipse regardless of the plane's direction, and it makes it convenient for observations since the plane's direction can affect anything. So this is a graphic of the flight path on the day of the eclipse. The arrows show the general direction of the planes, and the circle up there shows the little loops, and those were the holding patterns that the planes took to stabilize things, to calibrate things, to get everything situated for the observation, because the planes had to be about 100 kilometers apart, and they're going over 300 miles per hour. So they had to be very precise with it. And it was a success. And we were able to get about 8 minutes of continuous totality versus the 2.5 minutes that a stationary observer would get. So this is the raw image of the eclipse with the corona taken by the planes in midwave infrared. And you can see here, I'm sorry you can't see my cursor, but on the right there is a solar prominence. On the left there's an active region. And we know that prominences are made of chromospheric material, which is about 10,000 degrees Kelvin. And the active region is up to 1 million degrees Kelvin. So they're different temperatures, even though they look about the same brightness on the in the picture, they have very different physics. This is that same picture, but it's calibrated and enhanced to see the structures which were hidden by lots of noise in the previous picture. There's been so few observations in this pass band, and no one knew what to expect by seeing, by seeing these two regions was really exciting, and also showed that IR was a great wavelength regime for observing these regions together. And the next step was to understand the nature of the mission from these structures, and so we can help understand the physical processes that are happening in these features. So we need another tool to help us understand this. So during the 2017 eclipse, the IR mission wasn't the only airborne mission. AirSpec with Dr. Jenna Samra had an airborne infrared spectrometer, and the mission was to observe coronal emission lines to better understand coronal heating. And AirSpec uses a slit spectrometer. So instead of taking spectra of the entire sun, they only take data along the slits here. And this is the picture of the positions of the slits, of the average positions of the slits taken by AirSpec. So onto the analysis of the data. My job this summer was to crack open these two data sets and see what we will find. And it's important to mention again that these observations are brand new. No one knew what to expect or find comparing these data sets. So they're similar in that they both take measurements in the IR of the solar corona, but they're different because they're taking completely different measurements. And they're not flowing at the same time. So there's some discrepancies that we took into account this summer. So here is the calibrated IR image again, but it has the AirSpec slit positions overlaid. And slit positions 2 and 3 go over the prominence and active region. And AirSpec can show us the emission lines from these structures in the infrared. And here is a plot showing the average spectra summed over each respective slit and its time. And this summer we peaked at all 4 positions, but we really focused on the prominence and the active region again, because they had the most activity and the most prominent spectral lines. And you can see on the east limb that there are some strong silicon lines in the active region, some really strong silicon lines in the prominence as well, and very prominent hydrogen lines in the prominence. So these spectral lines are valuable in the sense that they can give us a lot of information on what we're really observing and with these structures, and we'll get into that into the later slides. So this is a video of AirSpec during their observations, and you can see that the slit is moving up and down on these structures and not really keeping a single position over them. And a lot of people would see this as a problem, a very serious problem. But this summer, my mentors and I, we turned that into a strength, and we used the slit movement to better understand the spatial distribution of the emission and sample the spectra at different points in space. So AirSpec wasn't the only tool we used to help compare the data. The GO-SUVI and 304 angstroms specifically was a beneficial tool because this passband is very sensitive to cool chromospheric material, and it would be most sensitive to clearly showing the structure of the prominence. And here's the prominence with the AirSpec, with different AirSpec positions overlaid. And we use SUVI here as a reference to make sure things lined up and give us a reasonable understanding of what we were trying to probe with the IR, because this line is so underobserved. So to give a clearer explanation of the data analysis we did this summer, this is a graphic showing the AirSpec data cube consisting of wavelength, slit position, and time. And this is my first in-depth research experience. So this really helped me understand what we were doing when we were looking at different data. And the picture here is a spectrogram of position 2, which goes over the prominence. And you can see that there's with the position on the y-axis and the wavelength on the x-axis, you can see that there are lines here, which are very interesting on the solar limb. And what we did in order to get a better grasp of what we're looking at, we sliced the data horizontally to produce this graph. And this is the sliced data that I just showed you, but we can see which lines are what. And this is time versus wavelength. And we can see that the hydrogen line on the far right is the strongest line, and it's moving in and out. And what we did, we plotted the slit position in time next to the spectrogram to see that the hydrogen line was turning off when the slit position was moving south, and vice versa. When it was moving more north, the hydrogen line turned on. And that told us that we can exploit the slit motion to get spatial information and key spectral lines. And you can see faintly on the left, I'm sorry, again, you can't see my cursor, but there's a faint hydrogen line in the middle on the left, and on the far left, there's a sulfur line, a silicon line, I'm sorry, and a sulfur line in between those. And we did the same thing with all 4 positions, but again, the prominence and active region were the most exciting and the most interesting. And we did the exact same analysis. And this is the slice of the data of the active region. And you can see there's a very strong silicon line, which kind of overshadows the magnesium and sulfur line here. And you can see that we plotted the slit position next to it, but it doesn't deviate like the hydrogen line did. And that showed us that the silicon and the sulfur and magnesium they're pretty well dispersed around this active region. So knowing that we have all of this data, and which can give us so many things like temperature diagnostics, spatial distribution, spectral emission lines, and probably so much more, my mentors and I had an idea. We could use this data to sort of make images to show us what can be revealed with these particular spectral lines. And these slits are a clue to what's already there, and we can choose different spectral lines to help reveal these structures. So I have another graphic here, which kind of explains what we did to make these pictures I'm going to show you. So you can think of this like a blacked out picture that's only revealed if you can scratch the surface. And these scratches can be the different slit positions. And with careful manipulation of the data, we can see what's revealed with these specific lines to see what structure is underneath and to see where these lines are specifically emitted. And putting this data through a program and having the missing data be interpolated, we're able to see structure here. So here are pictures of the prominence in different wavelengths. And you can see each spectral line has a different morphology and spatial distribution. And we have the silicon 9 and 10 line overlaid here, the magnesium line in the middle, and the hydrogen 1 line on the right. And if you remember, the hydrogen line moved in and out. And that was interesting because we can see more structure with the hydrogen line here. And that's very interesting. And here are the same pictures but with the active region. The silicon line, if you remember the blue plot with the very strong silicon line, that's represented here with the silicon being very well shown, and the magnesium line in the middle, and the sulfur line, which is very faint on the spectrogram, it's very faint here again. So that was really interesting. So using these pictures, we can compare them against the IR image to compare morphology. And we're fitting these pieces together because we initially didn't understand why we saw the prominence in active region. And this is a possible opening to study properties of these structures. And if we had more time in the summer, we would dive into this direction and make direct comparisons in the IR and the structures revealed with the AirSpec data. And again, this is of the silicon in the active region. So onto the conclusions. I wanted to talk about some personal takeaways from this project. I had a very unique summer and a great experience with the REU program and my mentors. As I mentioned before, this is my first real in-depth data analysis or research experience at all. And it exposed me to a lot of new skills, specifically dealing with the data that had quite a few issues with it. It's good to note that not all data is perfect. And a lot of the summer went into understanding what the data was telling me and understanding, what the jitter was and stuff like that. So that was really interesting. I also want to give a nod to the REU program for still going on with this programming, despite being a very interesting summer. And then I also want to give a nod to my mentors for being awesome and having them guide me and teach me about this project. And I'm very grateful for the experience I had, and they really set the bar for my future research advisors. I'm very grateful for them. So back to the science. What did we learn? This summer we saw that there's much more in the data than we expected for both data sets. And we saw that bringing them both together can tell a story that we wouldn't have realized was there individually. And so we could also gain that showing that IR was a viable and interesting regime for coronal studies. And it's particularly well suited for eclipse science. And that can even open a new avenue for instruments that can explore the corona in ways we haven't previously been studied. And with what happened this summer, we can look at relative intensities compared to the total emission. It can give us an idea for how to do this again, but where AirSpec didn't take any data. And most importantly, we can point to future eclipses by knowing where we want to focus our efforts. We can know which lines are the most important. We can know which ones are the most interesting. We can know which ones carry the most information, and et cetera. This project points to the future in 2024, where the next total solar eclipse will cross the United States, and it can help us target the next observation along with improved instrumentation on both planes. I'll be 24 when this happens, and probably in grad school. So I'm excited to see what new strengths I'll bring to the future projects with the mentors. And that's everything.
Thank you so much. We've already seen many questions coming through.
I'll see if I can answer them.
All right. Marty, you want to lead the question session?
It helps if I'm unmuted. There was a question from YouTube about the solar cycle in 2017. Do you know what part of the solar cycle these observations were taken during?
I don't remember. I don't remember.
Yeah. Okay, so it's pretty active, kind of on the declining phase from cycle 24. So in another few years, it'll be on the rising phase of the solar cycle. So
Yeah,
it'll be interesting to see if there's any difference. Are there other questions from the audience?
I have a quick question.
Mm-hmm.
First off, nice job.
thank you.
And, so one of the ways you slice the data was in time.
Mm-hmm.
How was there? But you mostly looked at what you were presenting with spatial variation. Is that
Yes.
am I reading that correctly?
Yes. Mm-hmm.
So was there any time variation for in the minutes that were being observed, or is that just a way of organizing the data?
It was more of a way of organizing data. We didn't really look at it in that way. Just what the slip movement, I remember the video of the air spec movement, that really set us off into really keeping with the spatial distribution and not really slicing it differently. If we had more time, definitely would have done it, but yeah, you're correct in that.
Okay, great. No, yeah, okay, great.
Oh, thanks.
So Dan points out that these observations were taken right before the biggest flares of the cycle. So just missed it. So I have another question. So in the next eclipse, would you fly the same instruments, or would you like to see? Was there something that you wish that they had in this set of observations that you would like to have captured in the next set?
It's interesting because this is what we're doing this summer can really affect the instrumentation. It will really affect how we're going to change things. And especially with AirSpec, the 2017 data, as you see, like it moved around a lot and they didn't really like that. And so if we can show that, oh, it's not a bad, it's not as bad as you thought it was, that can really change the instrumentation. I can't give you a specific what I would prefer on the instrument, but I do know that this has a very significant effect on how things will change when the future eclipses and stuff.
Mm-hmm. All right, great.
So I have a quick question. So what's advantage to fly airplane instead of ground observation, or like observation that stays at the same spot?
This was unique because the airborne observations got above like 85 to 90% of the atmospheric air mass because these planes were built to be super high. And it's in airborne, on the ground, the atmosphere is going to absorb and emit different wavelengths. And so the IR especially isn't going to get down to the ground like that. And so that's why they flew the planes. And in space, it's also expensive, and the type of instrumentation can be limited in space as well. So that's why the airplanes were kind of like a good middle in between those two options, I guess, and cheaper, I guess. So.
Thank you.
All right, and don't forget to fill out the evaluations after every talk. Thank you.
Okay, our next talk is Drew Manning from Colorado College. And he's going to talk about the coronal dimmings and CMEs.
Great. Should I just go ahead and get started?
Sure.
All righty. Hi, good morning, everyone. My name is Drew Manning. I'm a rising junior at Colorado College. My mentor for the summer was Larissa Krishna from CU and NOAA. And our project for the summer is using quadrature observations from the stereo and SOHO satellites to identify the relationship between coronal dimmings and CMEs. It's a bit of a lengthy title, so let's jump right into it. Starting with CMEs. So coronal mass ejections are eruptive events where plasma is released from the sun. They have a wide range of velocities and masses. Velocities typically range from about 250 to 3,000 kilometers per second, whereas masses are generally in the range of 10 to the 13th to 10 to the 16th grams. And as these CMEs are released, they travel outwards away from the sun into interplanetary space. So here is a video of actually 3 CME events taken on the C2 coronagraph on the LASCO instrument aboard the Solar and Heliospheric Observatory on December 12th, 2010. So you can see these 3 events here. The most notable is coming off the western limb. And you can see as they grow, they kind of assume a light bulb shape. And so how they occur, so magnetic field loops emerge from the photosphere and are held in equilibrium of gravitational and magnetic forces and gas pressure. However, for various reasons, these loops can be brought out of their equilibrium and into a state of instability where the sides of the loop are kind of forced together, causing a magnetic reconnection, as you can see in this picture. Right here at this X, we're kind of seeing this reconnection where the lower portion connects and cuts off the upper portion. And this is what causes these bubbles, magnetic bubbles of plasma called plasmoids to be released. And that's what we see in the coronal mass ejection. So when coronal mass ejections reach Earth, they have the potential to cause some pretty detrimental effects. Of note is that they can cause power grid blackouts, cause outages in high frequency communication and GPS navigation, as well as cause some damage to spacecraft as well as astronauts. And you can see on the right-hand side of this chart that they are fairly frequent. There's roughly about 3,000 CMEs that hit the Earth every solar cycle, which is 11 years, though the majority of these are very minor events. However, you can see from this that it is very important to be able to effectively forecast coronal mass ejections, being when they arrive and the severity of the event. So in their wake, coronal mass ejections leave behind these cavities that appear dark cavities in the corona that appear dark in extreme ultraviolet images. And so these are kind of the footpoints of the CMEs, the regions where the magnetic field lines that make up this coronal mass ejection originate. So if you go back to this image, you can see kind of the footpoints from where this magnetic field loop arises. So those are kind of the footpoints. And coronal dimmings are generally detectable for a few hours, and they can appear as single, double, or multi-region phenomena. This kind of depends on how many footpoints there are and where the footpoints are located and spread out from each other. And over their lifetimes, these dimmings morph. So they typically grow and reach maximum area and then decay and shrink as they fade away, as they get towards the end of their lifetime. And they also can split into multiple dimmings and merge with other dimmings. So past research has been done in an efforts to quantitatively relate CME and dimming pairs by Dr. Krishna and Dr. Reinhard in 2017. However, this research showed little or no correlation between different properties of the 2 phenomena. And so it was hypothesized that this poor correlation was due to the observation angles at which CME properties were measured, which brings us to what we were doing for this summer. So by observing associated CMEs and dimmings during the quadrature period of stereo and SOHO satellites, we aim to identify correlation between the properties of these 2 phenomena in an effort to improve forecasting capabilities. So what sets this research apart from the research done in 2017 is that we are using observations taken from the quadrature period of the stereo and SOHO satellites. So the quadrature period between these satellites is when they are at 90 degrees away from each other. So if you look at this image, you can see they are not at 90 degrees away from each other. We also were using stereo A for this summer. So if you use your imagination and put stereo A right about here and relate it to SOHO, then you can kind of see the quadrature period between these two satellites. And that is the period where we took all our observations. So as stereo A, excuse me, let me find my cursor, observes dimmings kind of right around this area, their associated CMEs will come right out here, perpendicular to the line of sight of the SOHO satellite, which we use to view the CMEs. And so that gave us the optimal observation view of the CMEs, to allowing us to make more accurate measurements of CME properties. So we had a catalog created by Dr. Krishna and Matthew West of the Royal Observatory of Belgium, which cataloged associated CME and dimming pairs throughout the quadrature period of stereo A and satellite and SOHO, excuse me. And that was between December 2010 to May 2011. So starting with processing the CMEs, we wrote a code that uses procedures from SolarSoft package to measure the masses of CMEs using base difference images. So the way this code works is that it'll take the difference image and convert the brightness into mass, and then given a user selected region of interest, it calculates all the mass inside the region and then returns the mass of the CME. So here are some CMEs I was looking at this summer, some examples. As you can see, there's a wide variety of size and shape. Here on the left, we see kind of a big CME. Here, this one's a little bit smaller, but it has this really nice bulb shape that we saw in the earlier movies. And on the right, we see it counts. It's a little messy, but it's still a CME. So part of what I was doing was watching videos of these CMEs, similar to the video earlier in the slides, to identify kind of when the CME was most visible for mass calculation, as well as noticing if there were any kind of simultaneous nearby CMEs that I could look at so I could know where to select the correct region of interest, kind of knowing where one CME starts and the other CME begins. And so for extracting the properties from our coronal dimmings, we use the coronal dimming tracker, also known as CODIT, developed by my mentor, Dr. Krishna. And this allowed us to observe dimmings throughout their lifetime. So the way this code works is that given a user-selected region of interest, it thresholds different pixel values until it isolates the dimming. And once it's able to isolate the dimming, it tracks that dimming back in time to the point when the dimming first appeared. And from there, it goes back forward in time and is able to take observations of the coronal dimming throughout its lifetime. As it grows and then shrinks and potentially splits and merges, it keeps track of all of that. So here is a video of the output of CODIT. It prints out all these different, it returns a ton of different images, which we just put together to create this movie. So you can see the zoomed in section in the bottom. This dimming has a rather short ascent period. It grows into its maximum area fairly quickly, and then it takes some time to decay and has a much longer descent period. This is pretty typical in what we would see in dimmings. But yeah, let's see, gotta move back. All right, so for our results, so like I mentioned, we were using the catalog of stereo A and SOHO observations during their quadrature period created by Dr. Krishna and Matthew West. And from this, we were able to use 11 single region dimming CME pairs. We also, the catalog included double dimming regions as well as multi-dimming regions. However, to process those, that involves an extra layer of processing, which we did not actually have the time to do. So for the scope of this summer project, we only used single dimming regions, which gave us 12 events to look at, 11, excuse me. So from these 11 events, like I mentioned with the CME code, we only extracted the mass as the only property we took from that. But CODIT allowed us to look at several more properties in the dimmings. Of note is the lifetime, how long the dimming was observable for. The peak area is the maximum area the dimming reached. peak EUV mean is at the dimming's maximum area, how the mean pixel value, and then delta EUV is the overall change in pixel value throughout the dimming's lifetime. So here are some scatter plots that we pulled from comparing these different properties. So starting with the top one here, we compared the CME mass to the peak time EUV mean. Again, that's the mean pixel value at the dimming's maximum area. And we can see here there's a negative linear correlation. The Pearson correlation coefficient is negative 0.75. So that's a significant correlation that we were able to identify. Something else we also looked for was comparing mass against maximum area and dimming lifetime. And this Pearson coefficients were not significant. They were 0.28 and 0.15 respectively. However, when we calculated the Spearman coefficient, we did find some significant numbers, 0.69 and 0.58. So this points to the notion that there is a monotonic, wrote that down wrong, monotonic relationship between these different properties. However, likely due to the fact that we only had 11 events to look at, that relationship is not immediately clear. So hopefully future work we can better define what that relationship looks like. And so this also gave us the opportunity to compare dimming properties to other dimming properties and essentially confirm things that have already been found. So of note is this top left here, we see that dimming maximum area and dimming lifetime are positively correlated. There's a significant correlation between the overall change in pixel value and the maximum area reached by the dimming. The bottom left here shows a weaker, but it's a weaker correlation between maximum area and the EUV pixel value mean at maximum area. This one here shows a moderate correlation between ascent period, which is the time it takes from the dimming start time to the maximum area, versus descent period from the maximum area to the end of the dimming's lifetime. And finally, we see a rather strong correlation between the overall change in pixel value of the dimming and the lifetime of the dimming. So the darker we see the dimming get, or the greater the change of the brightness of the dimming, the longer it appears to live for. So for future work, we hope to expand properties. In particular, we hope to add CME properties such as width, velocities, and acceleration. This will give us the opportunity to compare more properties and hopefully identify some more correlations. And like I mentioned, we only were working with 11 events. So we hope to expand that data set first by adding in the double dimming and multi-dimming regions. And also we have another catalog of the quadrature period observations between stereo B and SOHO, which we hope to use to, again, expand that data set so we can more clearly see the relationship between various properties. And yeah, thank you.
A great talk, thank you. All right.
Okay, I don't see any YouTube questions. Are there questions from the audience?
I have a question.
Yes.
Great talk, Drew. Thank you. I was wondering if you could maybe explain, or if you have any idea of how this might be applied in the prediction sense. So you mentioned that this will help to predict space weather, and I'm just wondering if you can talk about that a little bit.
Yeah, I didn't dive too deep into that, so I'm not too sure off the top of my head. But I believe just by better understanding, since these CMEs can, that's actually a good question, and I am not sure about the answer to that. Thank you.
That's okay, don't worry about it.
Yeah.
So I have just a question is kind of just a practical thing on your plots. So, so the units on the delta EUV, is that?
That's data numbers.
Okay, it's in data numbers.
Yes.
All right, and so I was surprised that the two different correlation coefficients were so different. What's different about how those are calculated? I don't think I've ever seen one where, kind of the go from 0.28 to 0.69 with the same data set.
Yeah, exactly. We actually made this discovery yesterday where we realized we had incorrectly calculated the linear correlation coefficient, and so we were kind of scrambling to figure out what to do. But then, so the first correlation coefficient is how like the linear correlation, and that's the Pearson correlation coefficient, whereas the Spearman correlation coefficient shows how much of a monotonic association there appears to be in the data. So we kind of concluded that the relationship might not be a linear relationship as indicated by this correlation coefficient, but we do see that there is some sort of monotonic association there. So maybe it could be linear and we just need some more data points to fill that in, but that is definitely something we want to look more into as we expand our data set.
Right. To eye, it looks, pretty linear, but maybe it's the fact that it's a log scale on the y-axis is what.
That's what tricked us too. So.
All right, cool. Any other questions?
I would love to chime in for just a second here.
Yes.
So Claire asked an excellent question. So the whole point of this work, the work that was done 3 years ago and what we're doing now is try to understand the relationship between dimmings and CMEs, because it's the dimming that we see first. So by understanding the relationship between dimmings and CMEs, if we do find a strong correlation, a strong relationship, then by observing the dimmings, we can draw possibly some conclusions about what the CME might look like, how much mass is in it, how wide it is, and then we can possibly predict what the space weather effects could be experienced at Earth. So that's the main goal. And about the correlation, yes, we were looking at log scales because we have such a wide range of areas, and we have obviously the log scale shows it much better, because if we showed it on a real scale, it would be completely, the trend wouldn't be as visible. So that's why we calculated both the linear and the monotonic relationship between these properties. And so we found that in some cases, particularly with dimming properties compared to dimming properties, there was a linear relationship. But when we compared to CME properties, this relationship was more a monotonic, which means that there is a relationship, it's just not linear, which is still a really significant finding.
So there was a question from YouTube about the position of stereo A. I think the person was asking, that it's looking from quadrature, but perhaps they're used to seeing images from later in the stereo emission of the backside of the sun. So yeah, this is before it got there.
Yes.
All right, cool. Thank you.
Thank you.
All right, our next guest student speaker is Maya Fields. She's going to talk about the space weather preparedness. Maya, are you ready?
Yep, I'm ready.
Okay.
All right, well, good morning and hello. I just wanted to say, first off, thank you so much for allowing me to present with the REU students. It's a great opportunity for me that the Hollings program just didn't have. My name is Maya Fields. I'm from the University of Maryland College Park, and I'm working with Dr. Larissa Krishna this summer on the Life and Death Space Weather Preparedness Project. So To start off, I want to talk a little bit about space weather. So what is it? There are solar active regions on the sun that are defined by the strong magnetic flux concentrations. These areas cause solar flares and coronal mass ejections, which are two different types of space weather that we look at. Can this be dangerous? Well, sometimes yes. Flares can affect the geomagnetic field, which is the magnetic field around the Earth. And as a result, we see disturbances from space weather that impact technology that we use on Earth. Some of this technology includes GPS navigation, aviation, satellite operation, and telecommunication. So if you just sit and take a moment, like all of these technologies are things that we use every day and that people rely on. So having a reliable and accurate space weather prediction method will be really important for our society. For this project specifically, we are focusing on solar flares and not CMEs like Drew was talking about in his presentation. Flares are a result of instability in the magnetic field followed by a magnetic reconnection. As you can see in the bottom left image here, there are two different field lines, red and blue, with opposite polarity. And the closer field lines to each other is where the instability is happening, and they cause a reconnection for the lines to start going in the same direction as the polarity next to them. That's when a flare occurs. There are many other ways that flares also occur. There could be an existing loop structure in the magnetic field and another loop structure forms next to it that can also create an instability and a flare reaction. Or the magnetic field lines could twist and cause a break and a flare could occur there. We don't have an exact science for this is how a flare occurs, but these are just some ways that flares can happen. So what is the current method? Well, NOAA and the Space Weather Prediction Center have a current flare detection method that they use to issue alerts for space weather events. These alerts rely on the GOES XRS instrument, so they rely on the integrated X-ray flux from the sun. These alerts require a continuously increasing flux for 4 consecutive minutes. So this creates a 4-minute delay. So what this means is that after a flare starts on the sun, we don't alert the public until 4 minutes after because we have to wait for this increasing X-ray flux to have 4 consecutive minutes. This is so that we don't issue a false alert or give false notice because we don't want to cause issues here for us on Earth, like causing us to shut things down without any reason. But this does mean that if a flare is coming and it's significant, we won't know until 4 minutes after it starts. This method also cannot pinpoint the origin of the flare on the sun, or separate simultaneous flare signatures, or identify weak flare precursor signatures. So these are some things that we wanted to look at using our new tool, DEFT. So what is this new tool? This is the Detection and EUV Flare Tracking tool, DEFT. The instrument that we use is the GOES-R Solar Ultraviolet Imager, or SUVI. It has near real-time high spatial and temporal resolution observations and does this in 6 different wavelengths, the 94, 131, 171, 195, 284, and 304 angstroms. So for our project, we primarily use the 304 angstrom for the identification of flare signatures. And we also take a look at 284 and 195 angstroms. This is because the flare signatures are able to be identified the best in these wavelengths. The instrument also allows for 1 second and 5 millisecond exposure times and has anti-blooming protection. DEFT is a new detection method that can detect main stage flares and early EUV precursor signatures. And the early EUV precursor signatures is what sets it apart from the current detection method. The current detection method can detect these main stage flares, but isn't able to detect these early precursors. We are also able to see imaging, which enables flare location identification. The current method that we are using for flare detection doesn't allow us to see the origin of the flare, so we don't know exactly where it is coming from. And the location of the flare is important to space weather because flares that come from the center are more impactful for Earth than flares that come from the limb. These EUV signatures are very important for early flare detection because in some cases, we are able to see the signs of a flare 20 to 30 minutes before flare even happens. On the next slide is an example. So this is an example of the September 6, 2017 X9.3 class solar flare that happened. The video that I'm about to show you is from the GOES SUVI instrument in the 195 angstrom wavelength. As you can see halfway through the video, there will be a pop that shows the flare occurring. I'm sorry, it's taking a moment to load. So as you can see, there's a start, and right there was the flare. I can play it again for you to see. So right around 12:02 UTC is when the flare occurs in this video. On the right-hand side of the screen are our data from the DEFT tool. We saw a precursor at 11:27 UTC, which is around 30 minutes before the flare occurs. And we saw the first signs of this flare happening at 11:45 UTC, which is 15 minutes before the flare happens. The X-ray flux from the current method showed that the flare began at 11:53 UTC, which is 7 minutes after we saw the first signs, and the SWPSI alert occurred at 11:57 UTC, 4 minutes after their identification of the flare and 13 minutes after our identification. So using the DEFT tool can be groundbreaking and really important for identifying flares that are this magnitude much earlier. So for this project, we were looking at 50 flares selected from 2017. These flares included C, M, and X class flares. We used the DEFT tool to look at the precursors and main stage flares for each one of the flares, and each of them was semi-automatically identified, which I will discuss later in the slides. So over here on the right is an example of another flare and our precursor and main stage flare identification. This was a September 4th M-class flare. The flare occurred around 5:05 UTC, and our precursor was 4:29 UTC, and our identification was 5:01. So we would have been able to issue an alert 30 minutes before the flare happens, or 4 minutes before the current SWPSI method would have been able to. So here is a summary of our results. Below are the 50 flares for their precursors and their flare times compared to the magnitude of each of the flares. On average, we saw that the precursors occurred 24 minutes before a flare was detected. As you can see, there is a wide spread up to our data with a standard deviation of 13 minutes, but there's a large chunk of the population that is surrounding 20 to 30 minutes, giving us our mean of 24. And with more data, we will be able to see this shrink down and have a lower standard deviation. We also see that with the flare times, the average is around 0.1. And this means that on average, the DEFT detection occurs at the same time as the X-ray start time. Well, what does this mean? Well, this means that we are at least 4 minutes earlier than SWPSI's alert time out of 50 flares. The standard deviation for this data is 5 minutes, but that means that at best, we are 9 minutes earlier than SWPSI's alert time, and at worst, we are 1 minute later. So as I mentioned before, I wanted to talk a little bit more about how we identify our flares. We look for main stage flare signatures 0 to 20 minutes before the X-ray start time. This is the same flare that we looked at before in the video, the September 6, 2017 X-class flare. Down here is our identification of the flare at 11:45. We identify the flare by the changing of pixels over the threshold. We set a threshold for each of our pixels so that when the EUV intensity goes over it and changes by at least 10 pixels, we can register an event. So at 11:45, we saw the pixels go up to 251. So that's when we decided that was the beginning of the flare happening. Over here, we see the precursor signatures. The precursors we look for 20 to 50 minutes before the start time of the flare. We look in this range because 20 to 50 minutes is when we would think there would be a signature that's associated with the same flare that's starting at the X-ray start time. Anytime later than 50 minutes, we think may be associated with other activity in the active region or a different flare. In this image, you can see when we decided the precursor happened because there was a pixels of 173 over the threshold. And this image also shows you another quality that the DEFT tool has, where we can see simultaneous signatures at the same time. So here at the bottom, we see another signature happening with 3 pixels over the threshold near the center of the sun. And then the threshold up here is associated with the same flare over here in the right side of the sun. So when we're thinking about these pixel counts, we looked at both the precursor pixel count and the flare pixel count with compared to the X-ray flux or the magnitude of these flares. And we see that in both, there is an increasing trend in the number of pixels over the threshold with flare magnitude. So as the magnitude of the flare increases, we can assume that the pixels that we see over the threshold will also increase. And as you see, there is 3 outliers up here that we wanted to mention. These outliers seem to be apart from the population down at the bottom, which is why we decided they were outliers. They are 3 M-class flares that seem to be acting a little bit differently than the rest of the M-class flares. We know that 2 of these M-class flares happened in the same active region, running up to an X-class flare. But the 3rd M-class flare did not happen in the same active region as an X-class, so we are unsure why it had such a high pixel count. We are hoping that with more data and more time, we would see more results that either agreed with the population at the bottom so that we could get rid of outliers, or would give us a better idea of what actually is going on. So our future goals for this project are to identify main stage flare signatures within 20 minutes of the X-ray flare start time. We also want to identify flare precursors up to an hour before the start of the main stage flare and aim to forecast the magnitude of each of these flares. We will achieve this by fully automating DEFT, minimizing false detections, and continuing to expand the flare detection database to increase our accuracy. Thank you so much. Here are my references.
All right, very nice, very nice. Are there questions from the audience? I guess while they're thinking, I do have a question. So at the, I think at the beginning you showed where the observations are coming from. Was it Suvi?
Yes, it was Suvi.
Okay, so there's more than one Suvi in orbit now. Does that help at all, or can you just use one at a time?
I believe that will help. I'm unsure which one we are using or this data is coming from, but I think that having multiple Suvis will give us more data that we can look at to use in the future.
Okay. And the other thing that I thought was interesting was that the flare that you're showing is the one that happened right after Lauren's observations.
Oh, cool.
Right. That was the eclipse was in August. All right. Any other questions from the audience or YouTube? Yep. This was a great talk.
Thank you.
It's 12 o'clock.
Sorry.
Okay. I guess there are no questions from YouTube, and sounds like none from us either. Thanks.
Yeah, thank you.
All right. So it will be, we will have a 30 minutes break from now on. And we will be back 10:30 Mountain Time and 12:30 East Time. Yeah, see you soon.
And don't forget to fill out evaluations for the morning speakers. Thanks. Once you start putting on those arrows, they're everywhere.
Yes, I'm not sure.
Yeah, you gotta delete them. You gotta say clear them all, because otherwise, yeah, when you click to scroll, it's like no, not more arrows. I had the same problem yesterday.
Okay.
That's how I know exactly what's going on.
Yeah, I have to like go up somehow, but it doesn't let. Oh, okay. All right.
Perfect.
Okay, make sure I don't touch it anymore. All right.
Yeah, look at it. You can go to Eclipse. You can move Gordon to Eclipse office. Gordon be a candidate. Gordon be a candidate. पर उसका रूम ये बड़ा है। रूम तो बड़ा है लेकिन उसका वो बीच में है।
Can you guys see the second screen?
Yes.
Okay, good.
Hello, everyone. Welcome back. So our first talk in the afternoon will be Erica Bartosevich. Hopefully I pronounce it okay. And Erica, are you ready to present your machine learning?
Yes, I am.
All right.
Hello, I am Erica, and this presentation is on machine learning exploration of solar active region classification. I worked with Tom Berger and Brad of Space Weather Technology Research and Education Center. So our goal is to create a brand new classification system for classifying sunspots, and it is based on the pattern findings of machine learning. It is not based on anything currently existing. And this system will be more modern and objective way to classify sunspots, and will hopefully lead to a future with more timely and accurate predictions of CMEs. So a little bit of background. The current most popular system of classifying sunspots is the Macintosh system. Now, the Macintosh system is used for operational flare forecasting and was created in 1980 and was based on a much older Xerox system. At the time of its creation, it used continuum images only. Magnetograms at the time were only used for research, and that's just because they didn't take pictures as often as they do nowadays. And there is another popular system called the Hale system. And this system uses magnetograms as well, but it's not as often used in operational forecasting. So with both of these systems, they both share the same quirk in that they're subjective, and they are functional systems. Now, the subjectivity comes into play with the fact that it is a human-created system, and it is a human-measured system, meaning that a human looks at these images and determines their classification. And these classifications have what's called a climatological, they're used for climatological prediction. And so what this means is that based on the classification, the statistical history of that classification going off and becoming a flare is dependent on that classification. So due to the subjectivity, if you show 5 scientists, a sunspot and tell them to classify it, they might come up with 5 slightly different classifications, which would mean 5 different flare predictions. So this slide shows the Macintosh system, and as you can see, it has 3 different columns, and I'm not going to go too deep into how it's predicted, but basically based on the criteria of each column, a classification is made. So we trained our computer on what's called principal component analysis, or PCA is how I'm going to be referring it to the rest of this talk. Now, PCA is very hard to put into words, but so are a majority of forms of machine learning algorithms. And so for PCA, you load in a bunch of images, and they are sandwiched together into one big giant image. And then linear algebra operations are done on each pixel in that image to find the variance or difference within for each pixel. And this produces an eigenvector. And the eigenvector is the principal component, and it points into the directions of the variance, i.e. the differences. And so positive components and positive variance shows a correlation between the features. Components with little to no variance are dropped. So there are 2 different types of principal component analysis. The first type is supervised learning, and then there's unsupervised learning. And the main difference between these 2 is a labeled or unlabeled training set. So with supervised learning, let's use an example of faces. So you have a database with the names and the faces of movie stars and politicians, and you take 20% of that database, names and the images, and you put them into the PCA, into the computer. And so the computer will will look at all the faces, and it will make eigenvectors of those faces. But it will also recall what face goes to those eigenvectors. And so when you reload in an image, it will look at that face and look at the weights associated with those eigenvectors, and I'll go more into this in a little bit. And it will determine whose face that is and tell you, oh, that's George Clooney or that's George W. Bush. Unsupervised, you load in that training set, and it looks at the whole thing indiscriminately, just as before, but it won't remember what goes to what because you didn't give it a label. And so it just produces eigenvectors that show the main variance, the main differences between those images. So here is a visual example of the supervised PCA for the faces. So as you can see, you get these weird blurry blobs, and each of these images is the principal component. It is the eigenvalue. And so as you go up in component, you go up in complexity. And so the first couple look kind of blobby and strange. And then as you get down to 15, you start seeing the details of the face. And so when, for example, going back to the labeled face example, you show this particular set has a lot of George W. Bush in it. And you show it George W. Bush, and it will deconstruct George W. Bush's face into eigenvectors and eigenvalues. And the eigenvalues are those weights I was talking about. Basically, you multiply the vectors by the weights, and then you add them all together, and that's how you reconstruct the face to the best of its ability. So that is a simple breakdown of PCA. So how we prepared our data, we used SCO HMI radial magnetogram, magnetic field magnetograms. And so what that means is that, this is my little sun model. And so that means that they are pointing straight off from the surface of the sun. Now, we only chose images that go 68 degrees latitude and longitude, forming a little box of allowed degrees. And this is because of perspective and because of signal to noise. And so what this means is that as you are at the edges, you get a more warped look at the sunspot due to the perspective of it being a sphere. But also because these are radial images, they are coming towards the viewer. So let's pretend you are the SCO telescope taking these images. You get the best view here, while the sunspots here are warped. And because the radial magnetic field is going this way, you get the best view here compared to at the poles and at the limbs. So that's why we ignored any images that were taken at those points. We also made the images uniform by making sure the leading polarity was positive. So any images that were in range and had a negative polarity were flipped, and images were also resized to be 512 by 256. And this was simply just because the PCA we are using expects same size images, so we resized them to make them the same size. So this is a video, and it appears to be growing, but it actually is just the image being taken as it goes over the limb, across, and then back over the limb again, to east to west being tracked across the sun. And so that's why you get this weird growing effect to this video. And it's also why it appears to shrink, and that white stuff that appears to come in and come out of the frame is actually the void of space as the sunspot goes over the limb. So when you put uncleaned images into the PCA, you get things like this. As you can tell, these are eigenvectors 1 through 8, and you can see, let me put on my little laser pointer, you can see that there are these arcing lines and diagonal lines throughout each thing. This one, you can see the arcing lines really well in the diagonal. And these are also repeating images. So, these are also repeating images. So you can tell this one is very similar to this one, which is very similar to this one, which is very similar to this one. This one and this one almost look like twins. And that's the kind of effect you get if you just feed it in raw. So when you apply the cleaning to the data set, you get this. So this is the top 40 components to the PCA. I mean, to these 500 randomly, so 50,000. Oh my goodness, 50,000 randomly chosen sharp active regions. And so these were the top 40. When we were coding this, we put in 40 components, and it pops out the top 40 components. And so what I'm showing you, this is the first 8, and then the second slide is the other 8. So this is in total the first 16 eigenvectors from these 50,000 randomly selected regions. And as you can tell, it's a lot cleaner. It does not have those arcs and those diagonal lines and random dark light regions other than what represents the sunspot. And here's the other slide. So reconstruction, as I mentioned earlier, PCA can reconstruct an image. And so this is the reconstruction using our 40 eigenvectors to recreate the sunspot given to it, which are shown to the left. So the left image on both of these examples are the original sunspot image, while the right is the reconstruction. And as you can tell, it did a fairly good job. It looks a little blurry, but again, we only requested the top 40 the top 40 components. If we told the computer to give us the top 1,000, we would get more detailed images, but that would be impractical for creating a brand new system of classification. And again, as mentioned earlier, it took those top 40 components, multiplied them by different weights, sandwiched them all back together, and recreated the image as best as it could. So, the conclusion. So, in the future, in the near future, we plan to do iterative PCA on all 300,000, a little bit more than that, but images available. And we have to use iterative PCA because we ran into memory RAM problems trying to load in every single last one of them, 100,000 of them. So 300,000 is definitely not going to fly. So we have to load them in batches and train it that way. We could also use these newly cleaned images for using autoencoder, a different form of machine learning in the future. But PCA is functional as a classification too. So let's say you have a sunspot image and you take the image and you put it into a trained computer, and that trained computer will break it down into its components and tell you the top, let's say the top 5 components and their weights. Those components and their weights could be the brand new classification system. And this new classification system could be similar to Macintosh in that it uses a climatological statistical prediction. Or we could take these eigenspots and, eigenvectors and put them into a more advanced machine learning flare prediction framework, like let's say using neural network input. So these are my references. And any questions?
All right, very nice. Michael, I had a question. He asks about why there is the bimodal structure of these images. Can you explain that?
Can you explain the term bimodal, please?
That they're all two kinds of things in these images.
So the black and white,
Yes, I think so.
Okay. Well, sunspots are usually, not always, some sunspots are unipolar, but a lot of the cases here, they're bipolar. So that's why it's black and white leading. Does that answer the question?
Right, because these are images of the magnetic field, right?
Yeah. Yes, these are magnetic field images. So like a fridge magnet or your favorite bar magnet experiment from elementary school. There's a positive end and a negative end, a north and a south end. Oh, I didn't know my mouse was poking in the corner there. Sorry. But so that is represented by white and black. And for the life of me, I cannot think of it off of the top of my head which one's represented by white and which one's represented by black. But because of that magnetic structure, that's why you get the usually bipole.
Right. No one can remember whether the black is into the sun or out of the sun.
Yeah.
So I have a question.
Great talk, Erica. Thank you very much. I am definitely not very familiar with eigenvectors and machine learning processes in general. And so I'm wondering what you could envision this process, how, like functionally, how this process might replace one of the other characterizations. So for example, would it be a case of that, you know, eigenvector 8 is the equivalent of a beta gamma delta spot or something like that? Or would it be a whole new way of thinking about sunspots?
I think it's a whole new way, because this is the computer just looking at these images and playing spot the difference and putting the most important differences, most common differences out towards you.
Okay.
So I don't think these are going to be equivalent or easily transferable at all.
Okay, thank you.
So I have a question. So I'm also not super familiar with the sunspot classification system, but does the classification of a sunspot change over time? I would think so, that a spot could become more complicated or simpler. Is that true?
Yeah, they can morph over time. I don't have this video in here, but I do have a video of a sunspot where it looks like just black, dark spots, and then all of a sudden white erupts from underneath. So that can happen while it's trekking itself across.
Mm-hmm, mm-hmm. And so also kind of a follow-up question of, you know, position on the disk, that you know, your viewing angle as it gets to the limb, does that make it look different in your classification system, or does that not matter?
I don't know, because we just didn't look at the limb, because those are just such poor quality images to look at. As you saw in that video, I can pull that up again. Let's go backwards. So as you can see, like right at the limb, you just get this weird opposite land squishy squashiness going on. So they're just such poor quality.
Mm-hmm, mm-hmm. Yeah, I mean,
yeah,
as a function of angle, right? Sure, right at the limb, you're looking at it sideways, but you know, when it's 45 degrees or something, yeah, okay.
Mm-hmm.
And so I think Michael has a follow-up question of maybe you can unmute Michael and ask your question.
Mm-hmm.
Okay, I guess it's more of a comment of so once your system is up and running, will there be overlap between the two systems, that yours will say, okay, this is now equivalent to this, you know, delta spot from the Macintosh simulation, or like will people just need to entirely abandon the old system?
I think I answered that a little bit with Claire, but I'm not 100% sure that it would be very easy to just put 2 and 2 together like that, because they're just based on 2 different things, right? Because the Macintosh was based on looking at sunspots and going, well, I, the human, see these patterns, and I, the human, make this prediction. But with this, you're feeding it into the machine, and the machine is going, I see these differences consistently, and here's what they are.
Mm-hmm. Okay, great job.
All right. Our next speaker is Katie Luttrell from Front Range Community College. Are you ready to show your presentation, Katie?
Yes. All right, can everybody see that?
It's still loading right now. Okay, yeah.
Okay, perfect. So, all right, well, thank you very much, everybody, for coming. And my name is Katie Luttrell, and my mentor is Dr. Wendy Karandi. And I'm going to be talking about magnetogram data augmentation using deep learning. So my project is about solar flare prediction. And a solar flare is a type of space weather. It is a sudden, violent burst of radiation from the sun. And this is important to predict because phenomena related to solar flares can cause radio blackouts, which can negatively impact GPS networks. It can interfere and cause blackouts with air traffic, HF radio communications. It can cause power outages and can impact the health of astronauts in space. So it's important to be able to predict when a flare is going to happen to prepare for its effects. And solar flares can be really hard to predict. So scientists are using machine learning models to aid in the prediction of solar flares. And for these to be successful, it's important for there to be a large quantity of training data, as well as a wide representation of the different types of solar phenomena within that training set. And so the focus of my project is to provide that. So I'm working with a type of image called a magnetogram, and that image shows the magnetic fields of the sun, the locations of them, the polarity, and the strength. And current solar flare prediction models are using the SDO HMI magnetograms to train. And that is the image on the right here. And those are from 2010 to present. They have the cadence of 45 seconds, the resolution of 0.5 arc seconds per pixel, and 4096 by 4096 pixels image size. And then we also have over here MDI magnetograms, and that's a historical data set from 1995 to 2011, which is also going to be very important in the project because of the dates it covers. But it does have the cadence of 96 minutes, the poor resolution of 2 arc seconds per pixel, and the smaller image size of 1024 by 1024 pixels. So there are only 10 years of the HMI data, and that's not even one complete solar cycle. So I am working to expand that amount of data. And my goal is to be able to augment the existing set of HMI magnetograms with synthetic magnetograms based off of the SOHO MDI magnetograms. And then to accomplish this, I will be using deep learning that trains off of the year of overlap between these two types of images and learns to translate the MDI magnetograms into synthetic magnetograms, which are comparable with the HMI magnetograms. And here under synthetic magnetogram, I have an image that some of my training has produced. The project is still in progress, so it's not fully trained, and that's why it kind of looks a lot different than the HMI magnetogram. But as the training progresses, it will look better. So here I have a graph showing the last 2 solar cycles and our current solar cycle, number 24. And a solar cycle goes every 11 years, and the sun gets more and has less solar activity. So currently, the HMI magnetograms span from 2010 to present, and you can see here that that doesn't even cover an entire solar cycle. It only covers a partial amount of solar cycle number 24. But the MDI data goes from 1995 to 2011, so it completely covers solar cycle number 23. So with the time period recorded by the MDI and HMI magnetograms combined, we have almost 2 full solar cycles, and we're able to show the wide variety of solar activity, and there's 25 years of data. So in the middle overlap period here, this brief 1-year period is what I'm using to train and to convert the MDI data into a more high quality, more usable data that is a lot more like the HMI data. So to do this, I am using a type of deep learning called a generative adversarial network. And in particular, I'm using a pix-to-pix GAN because I'm going to be doing image translations. So the difference between that and your normal GAN would be that the input is going to be data instead of random noise. So it's called an adversarial network because there are 2 parts to it that are adversaries to each other and are competing against each other. And I'm going to go into that a little bit more and the structure of a GAN. So the MDI image is our input. It goes into the generator, and the generator does mathematical operations that are changing to each of the pixels to have it output a synthetic image based on that MDI image. Then 2 pairs are made. For the same dates, we have the MDI image and the synthetic image that was produced off of that input, and then another pair of the same MDI image and an HMI image that was taken at the same time. These 2 pairs go into the discriminator, and the discriminator is the second part of the network. And the discriminator's job is to decide whether the pair is a synthetic pair or an actual MDI HMI pair. Then loss is calculated. The loss for the generator is going to be the difference between the synthetic image and the HMI image that it's supposed to look like. And there'll be 2 different types of discriminator loss. One to see how well the discriminator can identify a synthetic pair, and the other is to see how well the discriminator can identify what a real pair looks like. Then the loss is used to update the weights. The weights are those mathematical operations performed to the pixels that I talked about earlier, and those change little by little to make the outputs better and better. So my data I got from Stanford's Joint Science Operations Center for the MDI and HMI images, and I got them from the year 2010 because that is where the overlap is. And on this graphic here, you can see what I was able to get. The red dots show where only an HMI image was available. The blue dots show where there was only an MDI image available. And the purple is where I was able to get a pair. And I have about 4,200 of these pairs. So pre-processing. Before the images go into the GAN, some things have to be done to them. I resize the MDI images to be 4096 by 4096, just like the HMI images, so that there can be some parallelism in the UNet, which I'll talk about a little bit more. And another big issue is that the images, everything that was not in the circle, which is the sun, was not a number. And this was causing the generator to output an image that was completely not a number. So to remedy this, we made the background just a consistent arbitrary number and added a mask, which was another color channel, which had the area where there is data as a 1 and everything else as a 0 to kind of show what's important and what should be ignored. So back to the GAN, I'm going to go in a little bit more in depth about what the generator and the discriminator do. So the generator is an encoder-decoder model that uses UNet architecture. And the UNet, it's called that because it looks kind of like a U with the image size starting big, getting compressed down, and then back to the same size. And there's the parallelism of each side of this. And there are 3 parts to it. There is contraction, bottleneck, and expansion. And this part over here on the left is the contraction, where it is downsampled and getting smaller and smaller and more compact by throwing out any non-essential information. And this happens by using convolutional layers and an activation function. The bottleneck in the middle is where the data is at its smallest size before it starts getting upsampled. And in the expansion area over on the right, the image is getting upsampled, which is basically the opposite of downsampling, and it's concatenated with the parallel downsampled image, and together they are activated. And then out comes the synthetic image. And I'm going to go a little bit more into how it does this. It's not magic, it is math. So the generator uses these 3 activation functions. And an activation function is supposed to kind of imitate brain functions, and it decides whether a neuron should fire or not. So for the downsampling, we use leaky ReLU. For the upsampling, I use the regular ReLU. and you can see it starts to fire at 0. And at the very end of the generator, before the output image, we use hyperbolic tangent to activate it. And it's used to scale every pixel to be between -1 and 1, which is how the image comes in. And every pixel is one of those numbers, and it represents a different shade or different color, which makes up our image. The other part is the discriminator, and its job is to decide whether a pair that it receives is a legitimate HMI MDI pair or a synthetic pair that was made by the generator. And it also uses convolutional layers and leaky REU activation. But another thing it has is at the end, its activation function is a sigmoid. And you can see here it's bound between 1 and 0, which is important because the discriminator is deciding whether an image is real or synthetic, true or false, 0 or 1. So that's why we would want to use the sigmoid. And then below, this other equation is binary cross entropy, which is what I'm using to calculate loss. I remember that loss is the difference between the output of either the generator or the discriminator and the ground truth. And this was sometimes called log loss, and it's showing the logs of the probabilities that it'll be either true or false. And in my model, I've slowed down the loss weights for the discriminator so that it updates at a speed more similar to the generator. So training. The model is trained using pairs of HMI and MDI data from March 2010 to January 2011. The rest of it in the overlap period, I am saving for validation. And the discriminator is given a real pair and a synthetic pair with labels, and the generator is given a real pair. And then the loss is calculated and used to update the models, and the process is repeated. And here you can see some images that it output. After it goes through a certain number of iterations, it saves the model, which has how the weights are at that moment, and it outputs one of these to show how the progress is going. And at the top, we have the MDI images, which are the inputs. In the middle are the synthetic images that model predicted that the HMIs would look like. And at the bottom, we have the HMI images, which is the truth and how they should look. And you can see here on the left, that's after not a lot of iterations. The synthetic images are nothing like they're supposed to be. After some more in the middle, it's got the shape right. And then on the far right, it's starting to show the characteristics in the active regions. And I'll zoom in a bit more so you can see that. You can see here that it's on the right track. It's showing that there's an active region in the correct spot after it's been through several iterations. So results. This project is still in progress. I'm going to be continuing it this fall. But here you can see an image that was in output during the training showing the MDI, the synthetic, and the HMI images. And I'm on the right track because you can see that shows the features there. But of course, once I've completed all of the training, which is one of my next steps, I've only done a couple of practice rounds so far. I will be looking to see how it actually works using the validation, because this synthetic image was produced off of an MDI image that it's seen before during the training. But next steps will be to finish training, do some validation, update the GAN so that it gets better and better and does the translations more accurately so that the synthetic images look a lot like the HMI images and show the correct features. And then once that is perfect, we'll be translating all of the images from 1995 to 2010, all of the MDI images into these synthetic magnetograms, and it will be used to improve solar flare predictions. So thank you very much to the Boulder Solar Alliance REU program, to LASP, to my mentor, Dr. Wendy Kurandi, and to the National Science Foundation, and then my institution, Front Range Community College, and CU Boulder, where I'll be going in fall. And this research was supported by the National Science Foundation REU program. And yes, I can take any questions now.
All right, great talk. there are a couple of questions from the chat earlier. Jake asks about your loss function. Can you describe your loss function a little bit more?
Yeah, let me go back to that.
Mhm.
Where is it?
I think it was early.
Oh, there it is. Okay. So this is binary cross entropy, the also known as log loss. And the n is for each pixel, and within each log is true or false. So it's the log of the probability. The p is for probability of whether it's going to be one or the other. And that's about as in-depth as I can explain it. So
all right.
Hopefully that satisfies that.
Yep, yep. And if you can go to your pre-processing slide.
Mm-hmm. There we go.
Michael has a question of why did white become black and black become white?
Right. So I'm just using that to show that kind of binary layer. So in the circle, the black part, I'm putting a 1 there, like a true, to say this has data, this is important. And then the white part is a 0 to say this is not important, please ignore this.
That's your mask, the
Yeah.
sort of bottom image on the right. But in the magnetogram part also seems to switch polarity, right?
Yeah, it looks like it does. That is a really good question. I think that one of these images was. That's a good question. I don't know.
Okay.
I know that these images are from the same date. I think maybe one of them I used in HMI and the other one I used in MDI, perhaps. Oh, that's a good question. I don't know.
Okay. It shows he's got a sharp eye. He has another question about when you're updating the weights. Can you explain a little bit more about the logic that decides how to update the weights?
Yeah, so it's using the loss to update the weights. So I don't know the exact way it does it. I'm using a nice TensorFlow package that does it for me. So but to my understanding, it's looking at like this is the difference here. So like maybe like this part has a big difference. So push it a little more this way, push it a little more that way, to my understanding. I watched a couple of videos on kind of like how it does like the generator and discriminator would work and how like those like the convolution works. And basically I know a lot of the time it has like some sort of number that it'll multiply each pixel by, but there's a bunch of layers and it's very complicated. And luckily I don't have to really know exactly what's happening there. It's kind of nice. But it just kind of like tweaks those numbers a little bit to the higher or lower, so that what's coming out is more like what we want, to my understanding.
Okay. So I have, I think it's part of your future work, right? Is that, so in the pre-processing where you just resample and interpolate the lower resolution images to the 4K by 4K, then ultimately you would want to compare the results of your output to just that resampling. So to see how much the AI really, the neural network added to just, resampling. So that will be interesting to see.
I'm excited. I'm very excited to see where this goes. There's been some setbacks along the way, so unfortunately I wasn't able to finish yet, but I'm really excited to do the future work and to get this up and working. So yeah, very, very exciting.
Yeah. Welcome to science. You never feel like you're finished. All right. Are there any questions from YouTube? Nope, there are not. All right. Well, thank you very much. That was great.
Thank you.
Please take a few minutes to fill up the evaluation form for Katie, and welcome our last speaker for this session, Santiago Rodriguez from University of Colorado, Boulder. Santiago, are you ready to show your presentation?
Yes, I am.
All right.
Should I start?
Sure.
Okay, so hello, my name is Santiago. I'm a senior at the University of Colorado Boulder, and during this summer, I've been working with Northwest Research Associates, and my mentors are Stuart Gilchrist, Katie Lika, and Karen DeSauer. And I'm going to be talking about modeling the solar corona, so testing nonlinear force-free methods with a magnetohydrostatic test case. Why is this not working?
You might have to just click on your slide window to.
So my cursor disappeared.
You may try to reshare your slides, like exit.
Yeah, can you try stop the sharing? Okay. I think it should work now. Okay. So first a little bit about the background. So you can think of the corona as the outer atmosphere of the sun, and it's a region that's very important to understand and study because it's where a lot of highly energetic solar events take place. So stuff like CMEs and solar flares. What you see on that top picture right there, it's extreme ultraviolet emissions that seem to be tracing magnetic field lines in the corona. But even though we can see these magnetic structures in the corona, we can't really reliably measure the magnetic field in this region of the sun. What we can do is what a lot of people has been talking about, and this is using the Zeeman effect to infer the magnetic field at the photosphere. That's what you see in the bottom picture in the form of a magnetogram. And so this motivates the study of static coronal magnetic fields, which recreate the magnetic field in the corona using this data that we get to this 2D surface, which is the photosphere. So a little bit about the equations and the models. The full magnetohydrostatic equations, which are equations 1, 2, and 3, are quite hard to solve. So first, I'll explain real quick what they mean. The first equation is the force balance equation. And that first term, J cross B, is the Lorentz or magnetic force term, where J is electric current density and B is the magnetic field. And the other two terms, so the gradient of P is pressure. It's accounting for the gas pressure forces. And finally, the last term is the gravity term, which is assumed to be constant in the minus Z direction, which is a good approximation for studying small regions of the sun. And then equation 2 is just Ampere's law, and equation 3 is Gauss's law, which we also almost always enforce to be true for these models. But these equations are very hard to solve because equation 1 is nonlinear when you plug in equation 2 into it. And you also have to worry about these other two terms. But it is known, or it's thought that the corona is in what it's called a force-free state, which basically is a statement that the Lorentz force is 0. So equation 4 right there. And you can also think about it as like the pressure and the gravity contributions to the force balance equations are negligible. And these equations are easier to solve, but still nonlinear and require numerical methods to solve them. And lastly, the potential field, which is simple, which is one of the simplest cases. It basically ignores current. And I put it there because sometimes or a lot of times it's used to create boundary conditions for the other two models because it's fairly simple to solve. You just specify a potential field and solve Laplace equation subject to boundary conditions. But the problem with the force-free methods, and that's what I'm going to be focusing on, is that it uses vector magnetogram data at the photosphere to specify boundary conditions and the initial magnetic field that's going to be used. But we know that the photosphere is not force-free. We know this because by considering a special form of Gauss's law, that involves the Maxwell stress tensor, which you can see right there is represented by that T. We can get the Lorentz force integrals in the volume above the photosphere. And if we calculate these forces, which has been done in a lot of articles, you realize that the photosphere is not force-free. And so there's an inconsistency, which I will be exploring, just basically trying to input data that doesn't match the assumptions of the model. So a quick overview of the procedure is to build a toy model of sunspots, which is basically a functional form for the boundary conditions of these equations, and then use it as input into a specific magnetohydrostatic model that I will talk about slightly later. And then use this solution to create boundary conditions to the force-free model and see how the force-free model can handle forced boundary conditions. And then basically compare the solutions using various methods of comparison that are listed there. What you see on that picture right there is a magnetic field being recreated using a magnetohydrostatic model and Gaussian sunspots at the boundary. So the z equals 0, that slice you see there, you can think of that as the photosphere basically, and that's the boundary that we're inputting into the model. So the specific magnetohydrostatic model that I've been using is a linear model. So I said these equations were nonlinear, but by making a certain assumption about the current, we can turn these equations into linear and thus make them easier to solve. So this model takes as an input the normal component of the magnetic field at the photosphere, which again is going to be taken from that toy model. This toy model again is intended to be very roughly speaking consistent with observational data, but it's not really very realistic. But for the purpose of the project, this is what we're using. And so by specifying this special current density, we get out a single parameter, A, that goes from 0 to 1 and lets us control the strength of the non-magnetic contributions to the force balance equations. And so setting this parameter to 0 should give us already a force-free solution that when we plug it into the force-free model, it shouldn't change much. And that's what you're seeing there in those pictures. That's the solution to a linear magnetohydrostatic model, and then a solution to the force-free model using the boundary conditions taken from the other model. And as you can see, the model changed a little bit, but it doesn't seem to have a significant change, which is a good sign. it's telling us that the control case seems to be working fine, but I did a more quantitative analysis later. And for the force-free model, the method of solving this is by Cartesian current field iterations, or Rad-Rubin method. Basically, this method takes as input an initial magnetic field, so the full three-dimensional magnetic field, which is usually calculated using the potential field and the boundary conditions found in the observational data. And you also must specify alpha, a boundary condition for alpha at one polarity. These equations you can get by manipulating the force-free equations. This alpha parameter is basically found because in the force-free model, J cross B is 0. This means that currents are now parallel to magnetic fields. And so this alpha parameter is basically just a constant of proportionality between the current and the magnetic field. And so you specify BK minus 1 and boundary condition for the alpha value, and you calculate alpha K using that first equation. And then you plug in those two values in the lower equation and you update the magnetic field. And you keep doing that until BK is equal or very, very close to BK minus 1, in which point you've found basically a solution to the equations. And also another one of the constraints that we enforce is that as these iterations happen, the magnetic fields at the 6 boundaries of the box match the solutions to the non-force-free model, so the linear magnetohydrostatic model. So I built this code to calculate the net Lorentz forces and the magnetic pressure above the lower boundary, again, using these force integrals, and build a simple test case to make sure the truncation error was scaling as expected against the mesh spacing. And since I used the trapezoidal rule, you can see we got as expected a linear fit in the log plot, and the power law index is roughly 2. So this is a reliable way of determining how force-free are the solutions of the models. So for example, when we run the magnetohydrostatic model, we want to see how strong are the forces before we use them. We use the fields as a boundary condition on the other model, so we can see how well it'll run in light of the inconsistency I was talking about before. So these are some of the methods basically to show the consistency of the method, and one is to check the convergence. So we can plot the change in the magnetic field as a function of iteration number. And once this number 10 to the minus 9 would be a reliable solution. And this means that the magnetic field is not really changing that much anymore, so it's converged by that point. And as you can see here, when A equals 1, which is the maximally forced case, it seemed like it was having trouble converging, but got to a point where it was so small that the change was just negligible, basically. And also, we want to check resolution dependence. So by increasing resolution and then measuring some physical properties, we want to see if these change, then we know that there's a considerable effect by the truncation error. So for example, here I increased resolution by 2, but the force in the z direction decreased by 4, which is exactly the scaling of the truncation error, which means there's probably a considerable influence here by the truncation error. And if we keep increasing resolution, this number should go to 0. Here's for some of the results. I did mean difference calculations and correlation coefficients, as well as the standard deviation. For these 3 test cases, cases, for example, I did the force parameter 0. When the force parameter is 0, the mean difference is way smaller than the other two cases by about 2 orders of magnitude, as well as the standard deviation. And the correlation coefficient is almost 1. This is good. This is telling us that the control case seems to be working fine, and the model is not really changing that much when using force-free boundary conditions. But as you keep increasing that, the mean difference gets bigger and the correlation coefficient gets smaller. Correlation coefficient, when you're halfway through the maximally forced case, seems to still be very close to 1, which I thought was very interesting. And something we might want to do is run more test cases between 0.5 and 1 to determine how this drop is happening, if it's like a sudden drop or if it's slowly going down. But the mean difference in the B fields is increasing as the force parameter is increased, which was expected since the inconsistency is becoming more important. Here I just put the Lorentz forces for the linear magnetohydrostatic and the force-free model, using the other one as the boundary conditions. And so most of these are very small, and probably a lot of them are due to errors. But what I want to focus is on the FC component, which is the biggest contribution. So basically, the closer it is to 1, the less force-free it is. And so if you see the force parameter, when the force parameter is greater than 0, when the force parameter is 0, the FZ doesn't really change, which is good. It's telling us that the force-free, again, is not changing much. But when it's increased, the forces do decrease. The FC force decreases by like 2 orders of magnitude in half case and one order of magnitude in one case. And this makes sense because the force-free model is kind of trying to make the field force-free. And so it's going to reduce the influence of these forces. But some of the forces did increase significantly, like Fx and Fy on the forced cases. And that's something we want to explore further. So for the conclusion, future work, what you see plotted right there are basically the maximally forced cases. That's a solution to the top one is a solution to linear magnetohydrostatic, and the lower one is the solution to force-free. So you can see there seems to be a dramatical change in the topology of the solutions. But we do need to do a more detailed analysis of the results to draw more conclusions. So this is kind of an unfinished work. Computing field line tracings and magnetic energy, as well as magnetic flux, are other methods that we will explore to compare these methods and to compare these models and find the true nature of their differences. And we also want to use more realistic boundary conditions and add more complex magnetic structures. So stuff like flux tubes. And we want to see how well can the force-free model really reproduce these flux tubes that we will see in the magnetohydrostatic case. Any questions?
All right, very nice. Questions from the audience or YouTube? I haven't seen any in the chat yet, but I do have a question. If you can go to your plot of the power law index with truncation error. So let me. I'm just trying to understand this. So the power law of 2 as a function of mesh spacing, does does that just represent the change in area of the grid? Because that would also have a be, square of delta x, or am I not understanding it?
So changing area.
Right. So delta x is a length, but then your grid
Yeah.
cells are going to be an area. So
No.
is that also a power law of 2 or not?
Yeah. So delta x. So in this case, delta x equals delta y, delta z.
Mm-hmm.
And so they should be the same.
So does that mean that the power law of 2 is what you might expect, or not?
Yeah.
I don't know. That's why I'm asking.
In all directions, it should be the same.
Okay. Are there other questions? Anything from YouTube? Looks like YouTube is silent. And any other questions from the audience? All right, great job. Thanks.
All right, please take a few minutes to give some feedbacks for Santiago, and we will take about half an hour break, and we will be back 12 o'clock Mountain Time and 2 o'clock Eastern Time. See you later. All right. Welcome back, everyone. We will have 6 more talks on space physics and solar physics. Our first talk of the afternoon session is Christian Razik from Augustana College. Christian, are you ready to share your presentation right now?
Yep.
All right.
Okay. Screen share?
Yes.
Okay. Okay. We good?
Yes. Go ahead.
Is my sound quality okay?
Looks pretty good.
Okay. So, hi, I'm Christian Mrazek. I'm an REU student here at CU Aerospace. And the subject of my research over the past summer was the exploration of the response of the thermosphere to geomagnetic forcing using a technique known as principal component analysis. So up until the launch of NASA's GOLD, or Global Scale Observation of the Limb and Disk mission, we haven't really been able to get a complete simultaneous global scale image of what's going on in the thermosphere, which is the uppermost layer of the atmosphere that we generally care about. Some people say it's the exosphere. I'm not going to get into that too much. So basically up until now, we've only had localized observations to work with, which is obviously a hindrance when you're trying to figure out how something going on near the poles is affecting what's happening near the equator and vice versa. But GOLD has changed this for us, and we're going to capitalize on this by performing a case study into the response of the thermosphere to a geomagnetic storm on a global scale. This has involved comparisons between thermospheric composition and temperature, between gold data observations and WAM, or whole atmosphere model simulations. And we've also looked into the correlation between the forcing conditions and the thermospheric response using principal component analysis, a machine learning technique. And on top of that, the forcing conditions we've got have come from AmGeo, which is a simulative mapping of geospace observations. So what exactly is GOLD? It stands for Global Scale Observation of the Limb and Disk, as I said. It's an instrument aboard a satellite in geostationary orbit, but what's really important to know is how exactly it works. It sweeps across either hemisphere of the disk, which is the area of the Earth, and the limb, which is the outer region of the atmosphere poking above the surface, and it observes this overall structure in various far ultraviolet wavelengths. In particular, it's looking at what's called the air glow, which is thermospheric emissions. And the types of emissions we see, you can see them up here in the corner, as well as some synthetic or simulated GOLD observations down here that I think might be a little clearer. And these help to tell us about the composition of the thermosphere. So there are 2 particular features we look at. One is the atomic oxygen line at 135.6 nanometers, which is this big feature right here. And then the other is the LBH bands, which is all these smaller bumps you're seeing. And these correspond to molecular nitrogen, N2. And what's important also about these LBH bands is that they respond to changes in temperature. And we're going to try to use a ratio of these emission features as a proxy for temperature. So just a few key concepts to go over for you to get the gist of this research. We're going to be looking at a small geomagnetic storm, or even just a period of mild geomagnetic activity that happened in November of 2018. A geomagnetic storm happens when there's a major disturbance in Earth's magnetic field caused by an outburst of charged particles and energy from the sun called a coronal mass ejection. And we're going to quantify the period of the geomagnetic storm with the KP and DST indices, which are measures of stability in Earth's magnetic field. after that, the instability in the Earth's magnetic field leads to Joule heating. And this is the main method of energy transfer into the thermosphere during geomagnetic storms. It particularly converts the magnetic energy into thermal energy, which is going to heat the thermosphere near the poles. And Joule heating is estimated with AMGEO, the simulated mapping of geospace observations. And the result of the Joule heating, which is this geomagnetic forcing we're referring to, and the result of it is the response of the thermosphere in terms of both temperature and composition. And in order to quantify composition, we're going to look at something called the O/N2 ratio, which is literally just the ratio of atomic oxygen to molecular nitrogen in terms of number density. And the response will be determined using gold observations and WAM simulations. So here's our period of geomagnetic activity. We're looking at a time period from the 1st to the 15th of November 2018. On this plot, you have the KP index, and on this one, you have the DST index. The KP index increases when a geomagnetic storm occurs, while the DST index actually goes down and into the negatives. But what you'll see here is that the KP index peaks near the start of November 5th, and the DST index hits its lowest point around pretty much the exact same time. So we conclude that the peak of geomagnetic activity here happened around November 5th, 2018. On this plot, we have the total Joule heating produced by AMGEO, and this is over the time period of now the 3rd of November 2018 through the 7th inclusive. So on the x-axis, you have time. On the y-axis, you have the integrated or total Joule heating happening in either polar region. The black line corresponds to the northern polar region, while the red line is the southern polar region. And you can see that the southern polar Joule heating is noticeably stronger, which makes sense because it's winter or approaching winter in the northern hemisphere. But again, the real takeaway here is that the Joule heating peaks on November 5th, indicating that this is the time at which the energy transfer to the thermosphere is strongest. So now that we've looked at the geomagnetic forcing conditions, we're now going to look at the response of the thermosphere to this forcing in both gold and WAM. So first, to begin with, we're going to be using a ratio of the LBH emission features, as I said earlier, as a proxy for temperature. And here you have on November 3rd, the absolute value of the LBH ratio. And on this plot, you have the absolute temperature at 150 kilometers from the WAM simulation. And we picked 150 kilometers because this is the altitude that gold's observations are most sensitive to. But these red and blue plots that follow are the perturbations or disturbances from this initial value. And you'll see that the LBH ratio shows a significant response on the 5th. You can see a global scale rise in the LBH ratio. It becomes more red overall. But the WAM temperature strangely shows a very, very mild, a very weak response, if there's even a response at all. So this is something to definitely take into consideration. Next, we move on to the composition quantified with the O/N2 ratio. And again, you see significant differences between the gold observations and WAM simulations. So you will see that these two plots share north polar depletion, this blue area in the O/N2 ratio, around November 5th. But gold also shows similar depletion in the southern polar region, as well as enhancement of the O to N2 ratio, this red area in the equatorial regions. But these global scale features don't appear on WAM. So it seems like WAM overall shows a more localized response regarding the O to N2 ratio, whereas gold shows a global scale response. So here's where we're at so far. This isn't the end, don't worry. But a period of geomagnetic activity peaked on November 5th of 2018. The thermosphere's response differs significantly between WAM and gold, especially in the southern hemisphere. In particular, WAM shows a response that's very limited to northern polar O to N2 depletion, whereas gold shows a very clear global scale response. And we believe this is because WAM was forced with realistic KP and solar flux parameters, but the solar wind and hemispheric power, which is a measure of auroral activity, those two parameters were not quite realistic. Last but not least, we see that the LBH ratio seems to be a reasonable proxy for temperature, but again, the response for WAM could be better, and we think it's related to these unrealistic forcing conditions. So now we're going to move on to the fun part, which is PCA. So principal component analysis, or PCA, is it's a machine learning technique used to extract the main modes of variability in data. So it basically explains the data in terms of new parameters, which we refer to as principal components, that are linear combinations of the original parameters that were used. And this is done so that the early principal components each principal component explains as much information as possible that isn't explained by previous principal components, so they're orthogonal modes. And this is often used to reduce the dimensionality of data, because you can cut out the least important of these modes or principal components without sacrificing too much accuracy in the data. But what we're going to do is use it to look at the major global features of variability in the thermospheric response. So you can see that we've first done this on temperature, and on this plot you have the percentage of the total variance in the data explained, plotted with respect to the first 20 principal components that were extracted from the data. And you can easily see that the earlier modes always explain more of the variance than the later modes. And in particular, these first 5 modes seem to be the most important by far. They explain 64.3% of the total variance by themselves. So that's more than half of the total variance just in these first 5 modes. And then on this plot, you have what these principal components actually look like. So the top plot is just the mean temperature plotted with respect to latitude and local solar time. You can easily see solar noon around here, where the red spot is, because it's much hotter there than in the other regions. But you can also see the first 3 principal components here and their general structure. You can see some interesting features, like there seem to be some polar features on a couple, and some daytime features as well, like that blue region right there and here. So there's definitely a structure to them, and we'll look further into this in a bit. So now we have the PCA of the O to N2 information. And on this one, the early modes are even more dominant. You can see that the first principal component explains almost 30% of the data on its own. And then when we go to the first 5, it explains 74.9% of the data. So these modes are even more central here, these principal components. And then again, we have the mean O to N2 plotted with respect to latitude and local solar time, as well as the first 3 principal components. You can again see a different structure that kind of goes with some of the features we see in the O to N2, particularly this band of enhancement here near the northern pole. This is the part where we actually quantify the correlation between the response and the geomagnetic forcing conditions. So here we have the first 10 principal components of both temperature in red and the O to N2 ratio in blue on the x-axis, and then these bars are the principal, or they're the correlation coefficients between each principal component and the KP index. And this is very much the same, except the principal components are now being correlated with the Joule heating from AMGEO. And on this plot, you can see some of these values are larger or smaller than others. A value close to 1 indicates a positive correlation, close to -1 is a negative correlation, and then close to 0, it means there's probably no correlation at all. And that indicates that these correlations between the response and the KP index are overall stronger than those with the Joule heating from AMGEO here. And this is really the last major point before we wrap things up here. But this is looking at the progression of how dominant each of these modes exactly are. So you will see these principal component coefficients. They're not the same as the correlation coefficients. These are rather coefficients that these principal components that we see over here are being multiplied or amplified by. And that allows them to fluctuate and cause the variability that we see when this data changes. But you'll see that PC2 has a positive correlation with the KP index. This is for temperature, by the way, and you'll see that likewise has a positive correlation coefficient. And likewise, principal component 3 correlates negatively and has a negative correlation coefficient. These modes were actually smoothed out because they had a diurnal component originally. So these would fluctuate on a day-to-day basis, and this was smoothed out using a low-pass filter in order to reveal the overall trend and variability of the coefficients. And likewise, we have the same thing here plotted for O to N2, but there is one key difference, and that's that O to N2 response, its peak, follows the peak of the KP index by almost a day, which we don't see with the temperature response. We don't see any lag at all. And we've quantified this lag to be 21 hours, which is, again, almost a day. And it's not a response that we're seeing with temperature. So these are the conclusions that we made. There's still a lot of work that I think could be done into this, particularly obviously with getting WAM data that use the proper forcing conditions. But what we found so far is a period of geomagnetic activity happened over the period of November 3rd through the 7th of 2018 and peaked on the 5th. WAM doesn't simulate the southern polar O to N2 depletion because of unrealistic forcing conditions. The LBH ratio looks to be a reasonable temperature proxy, but the response of WAM could probably again be improved with proper forcing conditions. most of the variation of the O to N2 and the temperature is encoded in the first 5 principal components of those quantities. The variation of both temperature and composition with the KP index is stronger than that with Joule heating. And then last but not least, the O to N2's response to the geomagnetic storm actually lagged the peak of geomagnetic activity by 21 hours. But we didn't see any of this lag in the temperature response. And I think this is definitely kind of worms that could be investigated further, you know, sort of investigating the structure of this lag, because we see that it seems like there's 2 peaks on this, on some of these O to N2 coefficients. So it seems like we have something similar to this, but then there's a separate peak that occurs about a day after the initial peak of the KP index. And that's it.
All right, very nice.
So we've got so
Thanks. So there are a couple of questions from the chat. Michael I says, since all your signals are superimposed, would you think of using independent component analysis instead of principal component analysis? Did you discuss that at all?
We didn't discuss independent component analysis or anything like that. Most of our work throughout the summer, we really only concerned principal component analysis. Mm-hmm. Maybe that's something that could be looked into to improve upon this research, but we do see some evident issues with the forcing conditions that were used to drive the WAM data that we obtained. And you can see it in these O to N2 and temperature responses, because when the data is plotted, it doesn't quite show the response we expect. Obviously, models do have limits, so I'm not necessarily saying that by fixing these driving conditions that would solve all the problems, but I mean, that would be a major step in the future, you know, provided the time to work through it.
Okay, and kind of on a similar vein, Tom Berger asks, what did you use for your training set for the PCA?
For PCA, we used a function from a we used a function from a library to conduct this. I would need to look at what exactly we used, because I don't quite remember.
Okay. Are there any other questions from the audience or from YouTube?
I have a question. So would the Joule heating and the ON2 depletion impact the lower atmosphere?
So what are you referring to?
So here's thermosphere, right? And it has some depletion of the ON2 and also some heating temperature. And would those events impact the lower atmosphere, like dynamics or chemistry?
I mean, I think the response is definitely most noticeable in like the farther up into the atmosphere, you know, we end up going. But I mean, I wouldn't say it's out of the question, because a lot of these O to N2 changes that we see are caused by the circulation of N2. So we actually wanted to incorporate some of this data, but we couldn't quite get it to work, unfortunately. But there was wind divergence data And that's kind of helps to explain why these changes occur. So you have O to N2 being transferred between the upper and lower atmosphere layers, and that's what causes it to be enhanced in some regions where the winds are converging, and then they'll be diverging in this region because that's where you have upward circulation of N2.
Thank you.
Mhm. Okay, no questions from YouTube.
All right. Our next speaker is Hannah Ace from University of Vermont.
There we go. Okay. Are we good to go whenever?
Yes, please.
So hi, my name is Hannah, and I'm a rising senior at the University of Vermont, and I've been working this summer with Xiaoning Chu at LASP on a machine learning based model to study electron density in the inner magnetosphere, in the plasmasphere. So just to start off with some background on the plasmasphere and plasmasphere dynamics. So the plasmasphere is the cold, dense region of plasma extending from Earth's upper atmosphere to the plasma pause. And it's in a dynamic state due to the variations in geomagnetic activity. So particularly during geomagnetic storm, there's a process of erosion, plume formation, and refilling that occurs due to increased convection. So you can see in the photos at the bottom, the photo on the left here shows satellite observations of before and after a plasmaspheric plume after a storm. And then the photo on the right here is showing, so these lines are showing the alpha layers, which are co-located with the plasma pause, and they contract due to stronger convection during geomagnetic storms. And when they contract, it causes some of the plasma to be lost to the outer magnetosphere. And so you can see on the left the contraction of the cold plasma in the plasmasphere due to this increased convection. So looking at that process a little bit more, during quiet times when there's no geomagnetic storms occurring, ions and electrons in the plasmasphere exist in dynamic equilibrium with the upper atmosphere. And then when a geomagnetic storm occurs, it causes increased magnetospheric convection and the plasmasphere erodes, like we saw in the previous photos on the last slide. And like I said before, the plasmasphere erodes and some of the plasma is lost to the day side in these plasmaspheric plumes, which you can see in the photo on the right here. And so the plasma contracts to a lower L shell, or it kind of contracts radially. And then after erosion, there's this refilling process where low energy ionospheric plasma is drawn up from lower altitudes along magnetic field lines. And then when it is refilled, the plasma density increases and the plasma pause moves back outward. So looking at some of like the past plasmaspheric models, there are equatorial empirical models which use equatorial measurements where electron density is a function of L shell and then magnetic local time, or MLT, in the plasmasphere and trough regions. So their L shell and MLT are both positional measurements. So electron density is a function of just the two positional measurements. And the empirical function for trough and plasmaspheric densities are expressed either as exponential or power law functions, or some mix of the two. And then there are 3D empirical models, which are field aligned profiles, which use polar satellite or polar orbiting satellite observations. And there you have electron density represented as this function here, where it's a function of magnetic latitude and L shell, which again are both positional arguments. So both of these models are statistical averaged and, more importantly, static models. So they're neither time dependent nor geomagnetic activity dependent. And so there's not enough information generally there to represent the erosion and refilling processes that I was talking about in the last couple slides. So some examples of models that are time and geomagnetic activity dependent are data starved sparse satellite observations, which are very data intensive, and then two-dimensional or three-dimensional dynamic electron density models, the DN2D or the DN3D. So for this project, we developed a three-dimensional dynamic electron density model using a feed-forward neural network. And a model like this is important for a variety of applications, including the study of wave-particle interactions and wave excitation and propagation, and a study of dynamics of the relativistic electron in the outer radiation belt. So some people have already said some stuff about machine learning and that process, but I have this diagram here to talk a bit about neural networks, which was what we used in the model. So a neural network is a means of doing machine learning in which a computer learns to perform some task by analyzing training examples. So here in this diagram, we have the input layer starting on the left here. And for our model, we used the following solar wind indices as inputs. So we had flow speed, AL index, AE index, and SIMH index, all of which were functions of time. And then after the input layer, you have all of these hidden layers, which each contain neurons that receive data and send the data to the next layer. And in between all of those layers, you have these connections. And each of these connections have weights, which indicate how strong the connection is. So the input goes through all these different layers. And at each layer, the input goes through an activation function. So we use a sigmoid function here, which sort of takes the input and squishes it down to a number line between 0 and 1, so that the activation here is basically a measure of how positive the relative weighted sum from that neuron is. And it goes through all the different layers to get some output. And you can have any number of outputs, but for us, we just had one output, which was the log of the electron density. And so the weights and the biases in the model will initially be randomized. And so you have a data validation set of validation data, which you hold out from the model. And then a cost function at the output layer, which tells you basically how correct or incorrect the output is by comparing it to that validation data. So that in order to get an optimal performance for the model, you're looking to minimize that cost function. So for our input data, we used the electron density and the positional data from 4 satellite missions, CRESS, IC, IMAGE, and POLAR. And the positional data we were using was the L shell, the magnetic local time, and the magnetic latitude, which are kind of like r, theta, and phi in spherical coordinates. And that data ranged from 1977 to 2005. And then for the solar wind driving and geomagnetic indices that we used, we got those from NASA's Omni database, and we used flow speed, SIMH index, AL index, and AE index. And that data ranged from 1981 to 2005. And the data was interpolated to 5-minute resolution. So as mentioned before, we used a feed-forward neural network model. So for our model, we used 2 layers containing 30 and 10 neurons, respectively. And for training, the weights were adjusted based on minimizing the mean squared errors. So that was like our cost function. And we split the data up into 70% training data and 30% validation data, and then included early stopping and dropouts to avoid overfitting in the model. So dropouts randomly would disconnect a number of nodes during training to regularize the neural networks. And the training stops when the mean squared error computed on the validation set stops improving. So on the right, there's 2 figures here. The first one on the top is showing the raw data from the 4 satellites, showing the electron density versus the time. And then on the bottom, we have the model results versus the validation data. So this is the log of the showing the log of the electron density, and it's showing the model's results, what it calculated versus the validation data that was held out. And I'm going to show a clearer, more zoomed in image of this on the next slide, but you can already see kind of relatively how close the validation data and the model results are here. So on the right here, this is the same graph from that previous slide, kind of zoomed in to show how the validation or how the model results follow the validation data. So this is a randomly chosen set of data to show the data to model comparison. And then on the left, this figure is showing the distribution of error for the observed minus the model values. So for the models, we found the final mean square error was 0.1685. So that's the standard deviation was the square root of that mean square error. And then raising 10 to that power, we find the error for the density, which ended up being within a factor of 3. So it was 2.57 for the error for that. And this figure here shows the model's prediction of the electron density compared to the observed electron density. So the log of the predicted electron density is along the y-axis, and then the log of the observed electron density is along the x-axis. And this is a histogram of that relationship showing the strength of that correlation. So that is being shown by the light blue kind of scattered data points in the back. And then for a perfect agreement between the model and observed data, you'd be looking for a plot of y equals x, where the predicted electron density exactly matches the observed electron density at every point. So that light blue line, solid line that's graphed here is just a plot of y equals x to show how closely the observed versus predicted log of electron density follows that y equals x correlation. So to test the model, we apply it to known geomagnetic storm events. So these figures here were not created by me, they were created by my mentor, showing to test the DN 3D model. So on the top here, we have the evolution of the SIMH index during a geomagnetic event that occurred. And you can see this spike with the increased convection from the storm. And then in the bottom, these figures in the bottom, we see a generally similar trend of the plasma pause location evolution throughout the time. So at first you can see in the first quiet time figure, you can see the extended and symmetric plasmasphere before the storm occurred. And then you can see the erosion of the plasmasphere during storm main phase and early recovery phase. And then the formation of the plasmaspheric plume in the afternoon region, extending to the dayside magnetopause here. And then finally the recovery of the plasma pause during erosion and refilling of the plasmasphere. And so looking at all these figures, you can see that during quiet times and refilling and erosion to a degree, the plasmasphere is pretty symmetric. And so the more interesting period would be the plume formation here. So that's the feature that I attempted to recreate when testing the model on a different geomagnetic storm event. So this is our testing of the model on a geomagnetic event that occurred between March 20th, 2001 and June 10th, 2001. So on the top here, these are figures which are from the UVI instruments on the image satellites, which track the plasmaspheric evolution for 4 different time steps during this event. So it's June 10th here through May 28th, May 8th, and March 20th. And you can here, the Earth is seen in the middle with the white half representing the day side and the black half representing the night side. And you can see the plasmaspheric plume formation where the density is higher versus the lower densities around it. And so the 4 figures on the bottom were the ones that we created using the model to look at this same event. So you have L shell versus magnetic local time on the X and Y axes. So 2 positional coordinates, and then electron density plotted over them. And so you can see the spots where the electron density is higher and how it evolves. So that is representing that same plasmaspheric plume formation that you can see on the upper figures. And so you can see that it also follows the same general trends, or it tracks pretty closely with what was actually observed. And then these figures on the bottom here are the same, representing the same events on the same dates, but the coordinates are switched or converted to polar coordinates to show the same sort of display as you're seeing in the top figures. So we had to actually rotate these ones on the bottom by 180 degrees so that the day side of the bottom figures would match with the day side on the top figures. But you can see, again, if you look at, it's kind of hard because it's upside down now, but the higher electron densities here are towards the bottom of this scale with the more yellowish green colors. And you can see the plasmaspheric plume and its evolution throughout the 4 different time steps and how it tracks pretty similarly to the figures on the top, which are showing the actual observed electron densities for those times. So in summary, a plasma density model of the inner magnetosphere is really important because plasmaspheric density and composition strongly influence wave growth and propagation, as well as energetic particle scattering or dynamics. So for this project, we present a 3-dimensional dynamic electron density model using a feed-forward neural network, which takes spacecraft location and time series of solar wind and geomagnetic indices as inputs. And when compared with out-of-sample data, the model predicts satellite measurements with an error within a factor of 3. And when the model is applied to magnetic storms, successful reconstruction of the expected plasmaspheric dynamics was achieved. And that's all I got. For some reason, I can't hear Marty, even though it doesn't look like you're on mute.
Oh, I bet it helps if I put my microphone closer to my mouth.
Yeah, that helps.
Sorry about that.
That's fine.
All right, while we're waiting for questions to appear, I did have a question. So on your slide that showed the time series for the 4 satellites, back quite a ways. Yeah, that one.
Sorry, this one? Or
no, next one. Maybe next one. There it is. Am I interpreting that correctly, that the 4 satellites don't overlap?
Yes, I believe not entirely. So there were gaps in the data that we had to fill and interpolate. So
the I'm not sure how much calibration will affect your results, but so my question is, did your model detect that there was a different character of the data from one instrument to another, or did that not show up?
I know that we had to, when we combined all the satellite data, we had to fill the gaps there where it wasn't too big of a gap. There were gaps that if it was above a certain amount of time that wasn't filled, so I'm not exactly sure how much that would affect the model.
Okay. And your training, your 70% training, was that spread throughout the time interval, or was it like all in one block somewhere?
We used a function that split it randomly.
Okay.
So it was just 70% of the data randomly.
Oh, okay.
All the time.
That's cool. All right. Kennedy has a question on the polar plots of the geomagnetic storm. Can you explain the break that appears at the bottom and the top? I think like right at the terminator.
Yeah, this line.
Uh-huh.
That's a good question that I don't know the answer to.
That's a good answer.
Yeah. I'm not sure exactly why it's staggered like that. But
okay.
Yeah, interesting.
Yeah, I mean, it looks like it doesn't match up for some reason, so maybe
the
model goes one way or the other. All right, and then Jake asks, how many neural network models did you test? Did you try different numbers of hidden layers and so on?
So we tested one because it was my mentor Xiaoning. He already had tested it out previously, like that model. So we knew going in that it should work. So we didn't have to test several different input, like numbers of input layers and things like that.
All right, very nice. Any other questions from the audience or from YouTube? All right. No questions from YouTube. Great job. Thanks. Don't forget to fill out evaluations, everyone. I'll post the link again in case it scrolled off your screen. All right. Thank you.
All right. Our next speaker is Jonathan Roberts from University of Florida.
All
Jonathan?
right. Let's do, can I use screen? We're going to try this. Okay, and then, all righty, this should work just fine.
Looks good.
That over here. All righty, hello everybody. My name is Jonathan Roberts, and my REU project was the variation of small-scale solar magnetic fields with Hinode. My mentors were Dr. Ricky Eglund and Dr. Rebecca Sentinel. Alrighty, so no great solar talk starts without this famous quote, and it is, if the sun didn't have a magnetic field, then it would be as boring a star as most astronomers think it is, by Robert Leighton. Attributed to other authors also, but Leighton is the most famous of them, I think. And to begin, Hinode is a telescope that was launched in 2006, led by the Japanese Aerospace Exploration Agency, and onboard Hinode is a solar optical telescope with a mirror size of 50 centimeters. There are a few other devices, but in the project we don't use them. It also has an angular resolution of up to 0.25 arc seconds, and depending on the onboard machine that you want to use, the resolution goes up or down depending on what you use. But for this project, the Hinode SOT-SP, which is the Solar Optical Telescope spectropolarimeter, takes observations of the central meridian of the sun once a month, and it's been doing this since about 2008. And the sun itself is essentially just a big ball of hydrogen, and in its core, hydrogen atoms fuse to create helium, and then there are a few other processes that happen too, but by explaining them all, it'd take a class time, and I wouldn't do it as much justice as if you took a solar class. But essentially, the main thing that's happening is just two hydrogen atoms turning into helium, and with that, heat transfer also. And through that heat that's created through the hydrogen atoms colliding is pushed into the radiative zone, and then from here to the convection zone, where, as I say, the magic happens, because here in the convection zone, as the plasma itself is heated and some of the particles in the plasma are ionized, as they get heated, they move up, expel their heat, cool off, condense, go back down and get reheated again. And a great way to think about this, or a good example, is think of water being boiled in a pot, where as the water heats up, steam rises, comes out, cools back down, and the cycle continues. So that's essentially what's happening here. And in the convection zone, also, there's some atoms that are ionized, which means that there's just an electron not there. And so as these are moving, these create magnetic fields, and through magnetic fields, sunspots are created, which is this little spot right here on the sun. It also kind of looks like a cool dark region. And these sunspots are created through magnetism. Now, magnetism is just a force generated by charged particles in motion, and these are usually because of the ionized atoms in the sun that are moving, and usually these fields go from north to south, as seen in the BBC image above. And since the sun is not a solid, also I will mention now, please don't ever try to look at the sun. Please don't do that. I know most of us know this, but just in case. And since the sun is not a solid, it's a plasma. When it rotates, it actually has a thing we call differential rotation, which means that at the center towards the equator of the sun moves faster than it does at the poles. So with respect to the moving ionized particles that are moving throughout the sun, the magnetic field created by this also rips around the equator a little bit faster. So then a few other things happen and sunspots occur. But none of this happens without Maxwell's equations, credited to James Clerk Maxwell himself. And as an aside, the fact that magnetism is correlated to 1/c² is pretty amazing, and it is awesome. So if we look at the solar cycle, and we look at the magnetism, especially of the solar cycle, these are all images of the sun, magnetogram images, which are just maps of the magnetism of the sun. If we look at one over the entirety of a solar cycle, you can see at the very beginning and the end of the solar cycle, you don't get as much magnetism. It's kind of salt and pepper-like. And I will mention also that the yellow is magnetism coming at you. So just a magnetic field coming at you, and blue is actually a magnetic field going in. And as the solar cycle progresses, you get more magnetism as the peak of the solar cycle happens. And the solar cycle is also where the magnetic poles of the sun flip. So every solar cycle, the magnetic pole flips, and also does a few other cool features too, but we won't get into that right now. But as the solar cycle continues, you get different magnetization on the sun, and it peaks around usually the middle of the solar cycle. Now, these are also two magnetogram images, credit to NASA, SDO, and HMI, and the February 2020 observation is just the minimum of the solar cycle, and the April 8, 2014 is at the maximum. So you see, as the solar cycle progresses, the magnetism on the sun increases, and also the polarities, I will mention, you don't get one polarity without the other, so they are mixed together. Now, by looking at those two HMI images and looking at it over the solar cycle, you wouldn't, at least I wouldn't, be able to tell if there was anything cool happening with sunspots. So back in around the 1870s, I believe, Maunder and her husband created the very first butterfly diagram. And this is one, the image on the left right here is one of Hathaway 2010. And the butterfly diagram is essentially just counting the number of sunspots per latitude per unit time. And as the name suggests, in astronomy, we're really good at this. The wings, they look like butterfly wings. So as we can see, as the solar cycle progresses, in each iteration, it peaks and then goes back down, and the number of sunspots actually goes towards the equator, terminates, the solar cycle happens again. And another cool feature that I noticed that I like to tell is if you look around 1960 right here, when you count the number of sunspots, you can see that if there's more sunspots, the wings of these butterflies are really thick. That's just a kind of cool thing that I thought I'd mention. And if you keep counting the number of sunspots, they all look like butterfly wings. So since we know that sunspots are correlated to magnetism, one could think, okay, so let's look at the magnetization of the sun over the same period. And so we do. And Hathaway in 2015 produced this image, and we can see that the polarity of the sun changes and it flips during the solar cycle. We can see that at around 30 to 40 degrees north and south, they start forming, and then they go towards the equator. They terminate, they stop. We have a nice small period, and then this continues over and over again. And then there's a few other little concepts that I like the rush to the poles, where you can see the magnetism going to the poles and then flipping, and then the solar cycle progressing. Now, you should ask, how do we measure these fields? We can't physically be on the sun. Heck, we can't even look at it. So how exactly, or we can't visually look at it, how do we measure these fields? And the answer to this is actually polarization. Now, to give us some background, if an atom or an electron goes from one state to the next, so in this case, it's the 1s to the 2p state. If it moves up, it absorbs a photon. If it moves down, it emits one. So in this image, it's actually the electron is going from the 1s to the 2p state, so it's actually absorbing a photon. In astronomy, when we go to look at objects in the sky and we look at these lines, they're called absorption lines. And so the Zeeman effect, which this image displays right here, is actually when you apply a magnetic field to that absorption line splits. So the electron can actually go here, here, or here, which is a really cool concept. So to actually show us an example of this, if you go towards the center of a sunspot, where we know that there's high amounts of magnetism, even though it looks really cold on the sun, if you look at an absorption line, these are of two iron lines, I should say. And as we go towards the center of a sunspot, you can see that the Zeeman effect takes place, and you could see the splitting of this line, the absorption line. So then, to take this a step further, the intensity is the absorption line. And so the way we figure this out is we calculate Stokes I, Q, U, and V. Now, a great way to think about I, Q, U, and V is I is the light intensity, and it's the sum of the horizontal and the vertical. Think of you having a jump rope. I have the other end, and I'm going vertical and horizontal. Think about it like the wave coming at you. It's a great way to think about it. So if you're holding one, I'm going from side to side, and the wave is coming at you. That's horizontal. If I go up and down, it's vertical. So the sum of those two is the intensity. Q is actually the subtraction of the horizontal minus the vertical. U is 45 minus 135 of the linear polarization from 45 to 135. If you subtract them two, and V is the net circular polarization. So right coming at you, if you're holding one end of a jump rope, I hold the other, and I'm spinning it, and the wave is coming at you. As in this Wikipedia Commons image down below, the net circular polarization is the right minus the left. Now, Bello, Rubio, and Suarez had a few good examples of this. So I, Q, U, and V, and these are just two good examples. So as a recap so far, the sun is essentially a pink ball of hydrogen that creates its own magnetism. And this magnetism we want to be able to measure, but since we can't physically be there, the only thing we can do is look at an absorption line. And we figure this out through polarization, and we can calculate its magnetic field. Now, the way we do that is we use the radiative transfer equation. Now, this equation on the left side is actually Stokes I, Q, U, and V. But on the right, it's actually the atmospheric conditions in the sun. So since we can't physically be there, we have to solve the equation for the conditions, and some of the conditions include the magnetism on the sun. And since this equation is very, very hard to solve, and if I were to try to solve this, I'd have to do it about 2 million times per observation, and that would take a very, very, very long time. And we don't want to do it like that. And as a good advisor told me once, we might as well just use computers to do it for us. It's more fun that way. So we do. So we get computers to solve the atmospheric conditions for the Stokes IQ, U, and V that we observe, and we do that for every single Stokes IQ, U, and V we have. And for one observation strip, it's around 2 million different IQ, U, and V parameters, which I think is really cool. So when we apply this, we apply these to these observational maps, is what we call them. So these maps go from the northern hemisphere all the way down to the southern pole, so from the North Pole to the South Pole. And we take 20 observations of these per month since 2008. And the real cool thing about this is that the resolution on Hyundai is very good. So we can see all the little specks of magnetism. We can see the different polarities. So as we do this, as we observe from north to south, for each one of these pixels, I know it's very hard to see, don't worry, but for each one of these pixels, each pixel has a Stokes IQ, U, and V that we must solve. And when you slice them all together from north to south, in total it's around 2 million pixels and 2 million Stokes IQ and V parameters we have to solve for. That's why we get computers to do it for us. And so we do it for each observation since 2008. And just to show what we call a super magnetogram, I guess, would look like, it's kind of like this small strip on the sun right here. So then when you go to slice them all together, we get the magnetic butterfly diagram, which is my pride and joy now. So here, each little strip is actually an observation. And it's been doing this since 2008. And some things I'd like to mention, the white strips are actually data sets where there were less than 15 observations, and I want to spend a little bit more time looking at them first before I slice them in. But we get the main concept of what's happening. So we see at the very beginning of the solar cycle, there's just nothing happening. I mean, there are we can see the quiet sun really well. And the solar cycle really hasn't started yet. And I should mention the quiet sun is just areas where there's not strong magnetism. And so the things that we notice, we see the butterfly wings, and we see as time progresses, they get more towards the equator, they terminate, and then it's just quiet again. So as a comparison, we compare what we have to what Hathaway did in 2015, and we're looking, my map is correlated to his map from around 2010 to 2015, and we can see that my work is looking good, and we get much better resolution also. So then the question is, what's next? Now, the main thing that I need to do next, I will be doing this for my senior thesis in fall, since I graduate in fall. And the one thing I need to fix first is the pointing errors. So in each map, the FITS file headers say that there's a pixel at X location, but it's actually at Y location, Y degree latitude. And that I have to fix first. And Bruce Light, who is one of the main guys in the operation, has gladly given us his IDL code that he used for this. Thank you very much, Bruce. And then after that's fixed and the butterfly diagram is fixed, I'd like to collapse the butterfly diagram into total flux, northern and southern flux, to see over the time of the solar cycle if there's anything, if we can maybe sense what's happening and what may happen in the next solar cycle. And then we'd like to try to observe the asymmetries in the rise and fall of the flux in the north to the south to see if we can look for hints of the next solar cycle starting. And then from that, we'd like to look at the edges of those butterfly wings to see if, one, we can see if solar cycle 25 is coming, and two, if we can observe other irregularities in the sun. And then last but not least, we'd like to subtract the large scale flux to look at the small scale flux, and specifically because Hyundai is very good at looking, since it has such high resolution, it's very good at looking at individual areas in the sun. And with that, are there any questions?
All right, thanks. Very nice. I guess while the audience is thinking of their questions, I have to like come up with new questions because all of my questions appear on your what's next slide. But I will ask a question about your last bullet on here. Subtract the large scale flux. What does that mean?
So in the diagram itself, I go back, these main areas, there's this one strip right here. Do you see this like big red blotch? There's during this observation, and usually throughout 2014, there's like large chunks of just high flux. And we really don't want to, when we do statistics on this kind of stuff, when we want to look at the edges of the butterfly wings, and at the very beginning, we don't want that flux just overtaking everything. So our goal for the time being is after we get the magnetogram fixed with the pointing errors, we'd like to subtract out these large chunks to see if we can look in the quiet sun regions to see if we can get more insight as to what's actually happening in the sun. So does that answer your question, Marty?
I think so. So I'm just trying to think of the strategy of how to do that. Is it does it end up being sort of different time scales that, you know, that big red block lasts for a long time, so you distinguish that from shorter time scales? Is that how you're going to do it? I mean, I think there is the practical matter of how do you distinguish between large and small scales?
I think we haven't really talked about it much, but my plan would be look at the super maps that are correlated to these big magnetic regions and see if there's any place where there's sunspots that I just missed along the way, because Hinode sometimes takes maps from north to south, stops, looks at a sunspot, and then just keeps going. So maybe along the way that I can subtract out because we don't need in our data, because it's not the fact that we have such high resolution we don't need to see that well, because there's other telescopes that can do that that we don't need to, because we can look at the small scale field of the sun. So I think that is probably my main goal, is look at the super maps and try to find these large regions and then just subtract them out. Now, how we'll get there, I'm not totally sure just yet, but
okay, so there is a question from YouTube from Rahul Sharma. So they ask, have you managed to get the horizontal components of the magnetic field? You showed the line of sight component, but which is presumably BZ. Do BX and BY also show similar behavior?
I haven't looked at them yet. I know that the level 1.5 data has them in there somewhere. I just haven't plotted them to look at it yet, but let me actually write that down, because that's actually a cool thing I'll look at. So like, that's a good question. So I'm going to say we haven't looked at it yet, and then that I will, because that's very interesting.
All right, very nice. Any other questions from the audience?
There's a question from YouTube that I put into the chat window.
I see the one question. Is there more than one?
No, just the one.
Okay. Yep. We just talked about that one.
All right.
All right. Well, great. Thank you very much.
You're welcome.
All right. Please give, if you have time, fill up the evaluation form and to give some feedbacks for the students. We will take a break right now for about 20 minutes. We will be back about 1:30 Mountain Time and 3:30 Eastern Time. All right. See you then.
not there.
So just a reminder that we're still streaming on YouTube. If you did not mute yourself and you forgot to mute yourself, and you can do it right now.
Can everybody hear me?
Yes.
Okay. Also, is my cursor visible right now? Oops.
Yes, we can see
Okay.
it.
Gonna wait until 12:30.
Yeah, I can say welcome back, everyone. So we will have our last session here. The first speaker is Bjorn Larsen from California State University, Chico. Yeah, if you want, we can start. It's 1:30.
All right. Well, I'll go ahead and begin then. My name is Bjorn Larsen, and I am a senior physics major at California State University, Chico. And I've been working this summer with my mentor, Stefan Eriksson, at the Laboratory for Atmospheric and Space Physics on a project investigating the effect of solar observables on magnetic reconnection activity in the solar wind. Now, before I kind of dive into this research question, which we've been tackling, I'd like to give you all some background on magnetic reconnection and what is this data that we are looking at that we had measured in the solar wind. So many of us should be familiar with the idea of the uniform current sheet from introductory physics, in which we have a thin sheet of electric current, which creates parallel magnetic field lines which reverse in polarity as you cross from one side of the current sheet to the other, as given by Ampere's law. And current sheets can appear all the time within plasma physics, in the solar atmosphere, and within the heliosphere. But of course, current sheets in real life are not uniform. You always get non-uniformities, and you can get instabilities as well. So the question is, what happens if you have an instability within your current sheet and you have the current starts breaking up? Well, you can get really interesting phenomena such as magnetic reconnection here, in which the magnetic field lines from either side of the current sheet will bend in towards the instability, also which is classified as the diffusion region, and then they'll splice together across the current sheet, and the result is you have this inward flow of magnetic field lines normal to the current sheet, and then this outward flow that travels in both directions along the current sheet. And so another way to visualize this process is shown here, where you have the magnetic field lines which are breaking and mending, and then that specific point at which this occurs is also known as the X point, or if you are looking at in the context of a current sheet, the plane of a current sheet, it's also known as an X line. And the idea also is that you always have the magnetic field as well as the ionized plasma is always coupled together. So when you have these outward flows of magnetic field lines along the current sheet, it also carries with it this flow of plasma, which results in plasma jets, which are also accelerated by this transfer of energy, which takes place at the X line from magnetic field energy into plasma kinetic energy and thermal energy. And so reconnection jets are commonly seen all over the place in solar and heliospheric physics. And so the context in which we are looking specifically is within the turbulence of the solar wind. Now, these two diagrams here both show the same simulation of a roughly 100 square kilometer region of the turbulent solar wind, where the red and blue lines in the left hand side show the current density. And so we can see many of these thin current sheets, which I was talking about earlier. And then if you look at the right-hand side, we can see the lines represent magnetic equipotential lines. But then also every one of these spots where you have an X represents a location where you might have a reconnection X line. And each of these reconnection X lines have the ability to produce also a jet. And so if we're seeing this as a roughly 100 square kilometer or so region, and the solar wind is moving at usually about 300 kilometers per second, this means you're having reconnection jets could be showing up all over the place. And so the solar wind acts potentially as a great source of probing the behavior of magnetic reconnection. Now, the question is, how do we detect this data? So we're using data from the WIND spacecraft. And yes, WIND is actually the name of the spacecraft. And this is located at the L1 Lagrange point, which is essentially a stationary point 1/100th of the way to the sun. And so this takes single location measurements of the solar wind. And so if you look at this bottom left diagram, if this might show within a region of space a reconnection jet, where this blue region indicates plasma that's flowing outward toward the left, we can only see a cross-section of this jet using single location measurements. So what we see is this dotted line might represent where the WIND spacecraft is, and we'll see the cross-sectional signatures of this jet, which in the case of magnetic reconnection, we'll see this rotation of the magnetic field from negative to positive or positive to negative, as we could see earlier looking at just a uniform current sheet. But then we also get this spike in the velocity between the bounds of that current sheet. And that's typically at the alpha n velocity, which is essentially the maximum predicted reconnection outflow speed. So I show these same things again here, but this time we're actually looking at a real jet, which we were able to confirm using the data from WIND. And so we see this magnetic signature of this rate rotation. This is definitely one of the better looking jets that we got to look at. And then we also have this spike in the velocity. And the red and blue lines are a prediction that we put over this data, which is checking to make sure that this jet is propagating at the alpha n speed. And so this is this test that we run on every single one of the reconnection jets that we have identified within this WIND survey. And the survey code that is being used to identify all these possible jet candidates was written by my mentor, Stefan. And it has identified 4,945 unique candidate events within this 10-year data taking period of WIND's lifespan, which is a lot of reconnection jets to look at. And so right now, this data set is incomplete in terms of we have not gone through and confirmed every one of these candidate events. So what I have right now for my own analysis is I have only 931 jets over a 3-year period, which I'm using. And so having a big data set like this allows you to ask a lot of questions. And one that we were interested in is, how is jet activity driven as a whole? Because if you're looking at the majority of solar wind jets, majority of them are by themselves not going to have a major impact. You're not really going to have a major impact on the Earth or on the rest of the surrounding solar wind. But if you have 931 jets, then this could drive a lot more of the solar wind dynamics. And so this is kind of a big question to tackle. So I was looking more specifically at, are the presence of any solar observables correlated with the creation of reconnection jets? And one might expect this could be possible because, of course, the solar wind does come from the sun. So perhaps the conditions close to the sun when the solar wind was initially coming off of it would affect the behavior of processes such as reconnection out at 1 AU. So before we could actually tackle this question, though, we were really interested in, how do we know these jets that we are detecting are actually originating from the turbulence of the solar wind and not from some location closer to the sun? Because if you have a jet that's created close to the sun and then propagates out through the solar wind, well, you'll probably find some kind of correlation there between solar conditions. And I kind of have this illustrated what I mean right here, where at one time we have a current sheet in the solar wind or close to the sun potentially, where we have our reconnection X line, and the reconnection jet listed in red here starts moving down the current sheet. But then this current sheet is actually frozen into the plasma that's propagating radially away from the sun. And so at some later time, what you'll find is the jet has moved some distance further down the current sheet. And this is typically where we actually measure the reconnection jet. We never actually measure the X line itself, or if we do, we don't really have any way of confirming this. So what we're interested in finding is this DS, upstream source distance, of where the jet we are measuring was born. And so we can actually figure this out using just a couple of assumptions. First off, we assume that the solar wind is propagating at a constant velocity and that the jet is propagating constantly at the Alphean velocity, at which point we can relate this upstream source distance to the distance the jet traveled down the current sheet in terms of the Alphean Mach number, which is just the ratios of the two velocities. However, we don't measure this distance it's traveled down the current sheet directly either, so we have to make one more assumption, and this is involving what we call the reconnection rate, which is, if we assume that the reconnection rate is fast, then we can estimate this angle at which the jet cone essentially comes off of the diffusion region. And so what I mean by reconnection rate is it essentially describes the rate at which these magnetic field lines break and mend within the diffusion region. And it's a very big topic of reconnection research as well, which I'm no expert in and I can't really get into right now. But using this assumption, we can relate the normal width of these jets to the distance that it's traveled down the current sheet. And so now we have an estimation of this upstream distance in the solar wind where the jet was born in terms of things we can measure by the wind satellite. And so this next slide here, I just rewrite the normal width of the jet in terms of the normal component of the velocity multiplied by the amount of time that we measured this jet within the current sheet. And so plotted on the right here is the Alphean Mach number and then that normal velocity component and then the amount of time where this jet was measured for. So we can apply this formula to every single one of the jets that we have found thus far. And so on this next slide here are the results of this. And I have this plot where every single one of these points represents one reconnection jet. And along the y-axis is plotted the upstream source distance that we calculated for this jet. And again, this is just a rough estimation since we used assumptions, but it can give us a pretty good idea of how far away it must have been generated. And we don't need to perform any kind of fancy statistical analysis on this because we can just look at, okay, how far away was the furthest jet born? And in this case, it was a little over 1,500 Earth radii, which corresponds to 0.064 AU, which is only 6.4% of the way to the sun from the Earth. So really, all these jets which we're seeing in this survey are born nowhere near the sun. And this is important because then when we're doing this correlation analysis of solar conditions against the reconnection activity, this is telling us that essentially, this is telling us about the turbulent conditions of the solar wind that led to the generation of these jets. And so now here I have 4 plots, which are essentially showing the different pieces of data which we tested against each other. The topmost plot is the most important because this is the smooth moving average of the reconnection jet number over this 3-year period, where it's going from mid-2004 to mid-2007. And we used a moving average because it could show us more detailed variation than just using, say, like a monthly reconnection number would. And we couldn't use a daily reconnection number either because we don't actually detect enough jets yet. But this is what we use for kind of our dependent variable. And then we're also comparing this against the sunspot number, as well as the maximum daily X-ray flux, which is, this is using the GOES X-ray sensor, which is in a geostationary orbit around the Earth. And X-ray flux is an interesting parameter to look at because it's associated typically with solar flares on the sun. And then we're also actually looking at the smooth moving average of the solar wind speed as well, which is detected by wind. And you might be wondering, hey, wait a second, that's not a solar observable. And this is true, but it is well known also that the fast solar wind is typically above 500 kilometers per second and is linked to the coronal hole density on the sun, as well as fast ICMEs. So while it's not a direct solar observable, it tells us about conditions on the sun as well. So now I can show you all some fun correlation scatter plots. And on the left-hand side, we have the reconnection number against sunspot number. In the middle, it's against the logarithm of the X-ray flux. and on the right, it's against the solar wind speed. And so, as we might expect, because of just the turbulent nature of the solar wind, we don't really see any particularly strong trends here. The strongest one that we happen to see would have to be in comparing the reconnection jet number to the solar wind speed. But this is not quite the full story because not all of these jets are created equal. We have many jets which we actually detect within ICMEs, or interplanetary coronal mass ejections. And this is interesting to note because if we're using this total data set of reconnection jets to kind of probe the turbulent nature of the ambient solar wind, the environment within ICMEs is very different than the environment just of the ambient turbulent solar wind, because not only do you have a much higher plasma pressure, which is known to affect reconnection rates, or the rate at which you get reconnection jets, but you also have these shock fronts, which tend to produce reconnection at specific points within ICMEs. So how many jets do we actually have that are within ICMEs? Well, within this survey, we have a few. Again, I have this scatter plot where each dot represents one reconnection jet. But in this case, the red dots are representing jets that were born within ICMEs. And I've also plotted the solar wind velocity on the y-axis, because now we can see actually that many of these jets, which were created when the solar wind speed was especially high, were actually within fast ICMEs. So if we filter out just these few jets, it's about 50 or so jets, which were born within ICMEs, we actually see that our correlation gets a good bit stronger, still relatively weak if you were to compare against, any other correlation plot. However, given the fact that the solar wind is so turbulent to begin with, this is actually a pretty interesting result. And so it would be interesting to see also, once our data set is completed for this 10-year wind lifespan, if this result will carry over as well. Because as of right now, we still have kind of a relatively small sample size. So to kind of recapitulate on the main results, or the most interesting results I was able to find from this summer, first we have that these reconnection jets that we found within this survey are not born anywhere near the sun. So they're mostly result, we think, of just the ambient solar wind turbulence. And then we found no correlation between reconnection activity and sunspot number or X-ray irradiance. But we did find a weak inverse relationship between the number of reconnection jets and the solar wind speed, which again is linked either to these fast ICMEs or to the coronal hole density on the sun in the case of the fast solar wind. And so it'll be interesting to see if these results will hold out when we use the full data set. But for now, this is all I have. So I would just like to thank my mentor, Stefan, as well as to Marty, Claire, and Yun Chen for putting the REU program together, because it's been a very wonderful research experience. And does anybody have any questions?
All right, thanks. We had a little bit of a few comments in the chat about other ways of detecting these jets. I guess wind is near L1, right?
Yeah.
And so it's just detecting those that are within 1,500 Earth radii of the spacecraft location, right? I guess you can also detect them in the coronagraphs.
Yeah. Yeah, that's one other thing that I've we've talked about also, you can also try to image these jets as well. And for just this research project, we just looked at the magnetic and alphaenic signatures of these jets. But that'd be something that might be potentially very interesting to look at, is also looking at coronagraph data and see if we can get that additional source for imaging these jets.
Yep, Aline says that the result with the average reconnection height is fantastic. Good job.
Thank you.
Are there more questions from the audience or from YouTube?
None from YouTube right now.
Okay. Aline suggests that you compare it to a catalog that he published.
Yeah, this reconnection data set, eventually, once we're completely finished with it, is going to be released open to the public of where all of these reconnection jet start and stop times are. So other people will be able to go in themselves and find all these reconnection events. So that'll be really exciting.
All right, cool. Well, let's thank Bjorn again. Good job.
All right. Our next speaker is Atia Ali from University of Florida. Atia, are you ready to present?
Yes. Yeah.
Great.
Okay. Okay, so this is my presentation. It's about inverting, calibrating for the DKIST future coronal observations. So basically, the cryo-NIRSP is a cryogenic near-infrared spectropolarimeter, which is one of the instruments of the DKIST telescope, which is capable of sensitive imaging of faint infrared coronal spectra, and its primary goal is to measure the full polarization states of spectral lines originating on the sun at different wavelengths. For this, the team will work to develop software in Python, which will eventually or hopefully become a part of the main data pipeline for DKIST. Quantifying the accuracy of the spectral inversions compared to atmospheric calibrated observations will give insight to how to interpret the valid DKIST observations, because what's actually going on versus what I guess we'll be able to see from Earth, since it is a ground-based telescope, is going to be different due to some contamination. So the method we used all summer was using data of both fabricated pure and noisy sets that allowed us to compare the wavelength shifts and broadening properties that would help pinpoint or like help see where coronal contamination would propagate through the data set as a whole. From these findings, we hope to develop the specifications for like how we could like properly or more automatically read the DKIST observations. And this is working with the level 2 data processing of level 2 data processing developed at the National Solar Observatory. So we first try to understand the influence of noise of the pure observation data set we had, which is still simulated, so it's not a real observation, I guess. But so we computed the relative intensities of the linear and circular components of polarization, which helped in pointing out the components severely affected by the noise in this case versus not so much. This is correspondent to a few seconds of exposure time with the DKIST compatible parameters of resolution, aperture, sensitivity, and more. The table below shows the results of that. And at first glance, it seems that the ratios improve in the case of the noise influence data set, but this is misleading. The expected ratios are right there on the slide. So in this aspect, the noisy data is closer to what we'd see in reality. So the ratios for the noisy data set means that the data itself is compromised by the noise, and the first order magnitude apparent improvement in the V component means that the entire coronal signal in the V component is unreadable due to the noise level. Another way of kind of thinking about that is by using this table here. We see again that the noise V is much higher in magnitude when compared to what we're expecting. This shows it's basically unreadable, and that the I component counts at the line center are approximately doubling in value when accounting for the simulated noise model we used. The middle two components, Q and U, are basically almost equal in ratio, like almost with 1, and it's obvious that V is significantly amplified with a factor greater than 1,000. So significant noise disallows pure data to be completely recovered is the point of this slide. Yes, so observations of simulated coronal line emissions, which abbreviated to CLE, it comes from coronal line inversions, which was some code developed by Philip Judge and Roberto Cassini at the HAO and NCAR in '99. Basically, it's code that generates synthetic IQ, UNV parameters profiles in different emission lines of interest, mostly in the ultraviolet and visible ranges from a model coronal atmosphere, which would consist of thermal parameters, velocities, and magnetic fields to kind of mirror like observations or like realistic observations. We then started to use a cumulative distribution function, or CDF, to compare how the data for both sets, the pure and noisy, evolve, and we were able to fit it with a normal Gaussian distribution, as the plot shows, with the normalized spectral data. The coronal infrared lines might show complex features that might not be meaningfully fit by a Gaussian, but basically the CDF serves to visualize the overall summation of the spectra and what value it converges to. And it's just a simple statistical method. But yes, it's a little more flexible than standard Gaussian fitting, and we could kind of analyze the general line properties a bit more using the CDFs. Here, this is the iron 13 10746.8 angstrom line. We estimated a noise model applied to the pure coronal spectra with full polarization states. This is still with the simulated CLE data, and we could see we could quantify the solar and atmospheric effects that would ultimately influence a real data set. So the noisy normalized data started at a spectral value of approximately 0.5. It makes it clear that it has been contaminated, because otherwise we would expect the background signal to fade into 0, which it wouldn't in real life. And the trick to getting this was fitting it with an external noise signal computed from the observed Gaussian function, since we were trying to fit a summation imposed over a normal noise distribution. The wavelengths corresponding to the 16th, 50th, and 84th percentiles of the normalized distributions were recovered by statistical methods after that. And then these can eventually be used to derive the properties of the line, such as the full width at half maximum, or the standard deviation values for the distribution itself. Line shifts are then able to be calculated from these differences between the distributions from the 50th percentile to another chosen reference point. So these are the types of possible intensity distributions and how we use them to interpret spectral data. So we utilized the four different types of Gaussian fits, which are the normal, skewed, symmetric, and non-symmetric. We focused here basically on analyzing the behavior of the cumulative distribution functions over each of the four profiles. Yes, we can see that for the first one, the normal distribution, there are 3 regions of interest, meaning 3 different ranges of how the lines would move. The middle portion is approximately a linear function. The second, the skewed, something similar really happens, but obviously the slope is more steep for this one. We can learn from these how to identify more automated ways if a problem arises with the distribution of a specific data point. And here are the symmetric and non-symmetric ones, which the central depression, like the dip in the middle, makes it clear that this is exactly what this is versus, or how the data set would actually be set up. Okay, based on the output, the pixel, nope, sorry. So a set of effects can influence the shape of these emission lines or the CDF you would see in the spectra, be it atmospheric or etc. In a perfect environment, Stokes' eye should follow normal distributions, but it's pretty unlikely to see that in real life. Okay, yes. So atoms that make up gas in the stellar atmosphere are constantly in motion, and this is the motion that causes shifts in wavelengths, usually causes it to broaden. It can be like any combination of motion attributing to these, and the shifting of the ref wavelengths usually result in the observed spectral line from a specific stationary point being broadened a lot more than how it would be by its normal or natural atomic properties. Ultimately, the wavelengths we observe end up being a summation of the thermal, non-thermal, and instrumental wavelength parameters. Thermal broadening is just caused by the atoms in the gases and their intrinsic thermal velocities. Non-thermal velocity is smaller, and they don't have no significant relation to the temperature of the atoms in the gases itself. And it has an unclear relation with magnetic fields as well. Instrumental effects, or the wavelength changes caused by instrumental effects, are not an intrinsic property of the source, but it's mostly, as it says, instrumental. It just modifies the intensity that we observe in our telescope. For both the noisy and the pure data sets, we aim to compare how the line centers and full width of half maximums of the iron-13 profiles compared when recovered using either the Gaussian or the CDF approaches that I just mentioned. Using a linear interpolation function on the CDF values of the pure data set, we were able to recover the width of emission lines using the 86th and 14th percentiles to then find the wavelength shifts, and then we transformed them into line of sight projected velocities using the classic Doppler equation that's on the slide right there. Here we plotted a histogram of the measured line widths, which we just found using the linear interpolation function I mentioned, from all the pixels with coronal signal plotted, or it's plotted there. This shows that most of the pixels have widths close to the thermal width of the iron-13 ion, with a normal distribution of outliers as expected from a randomly generated data set. Okay. And then here we started the absolute wavelength calibration, which was, we started by restoring data for iron-13, silicon 9, and 10 lines from an atlas, and reading in their spectral data to start the calibration. Scaling data from the atlas and the coronal line emissions, we were able to obtain the following plots where the emission and absorption lines of the iron-13 and the other elements are imminent. The calibration for these data sets were done on a case-by-case basis, and we weren't really able to automate it since the candidates for the absorption lines to be analyzed, they should be far enough to avoid any overlapping, as we would see here, given you can see my cursor. So over here, the best candidate that at least I thought was at the 107.53 angstrom point, and then we appropriately ranged it so that it would like kind of be at the center, and then we flip it to make it appear as an emission line, and then we could observe the center of this using the CDF methods before, plotting this against the cumulative distribution function profile and locating the 50th percentile of it. We can see how the center is related to the locations from the wavelength data. This is the plot showing that, with the emission line being there, and then the center being there, and the CDF just being the little diagonal, since it's a summation, so it should grow exponentially like that. So we then calculated the atmospheric shift by subtracting the observed center from the calibrated reference for the center, And the resulting width from this shows how much the entire spectral data is shifted from its true values as we would read it from the sun directly versus to how we're receiving them on Earth. The estimations for Doppler shifts and velocities described above can be influenced by the atmosphere, which is not entirely stable, given columns of air masses and aerosols in the atmosphere altering and could even degrading the spectroscopic data, which we obviously aim to recover using the DKIST telescope. While we were doing this, it was still unclear if a wavelength calibration would be provided by the instrument team. So we used an atlas based on calibrated Kitt Peak Observatory observations in our infrared wavelengths of interest. That was kind of the end of how far we got this summer. So in the future, we hope to collaborate further and devise more improvements to what we did so far. The first being scaling the intensity calibration to account for varying atmospheric conditions, which would be, given that observations take a few hours to do, the changing sun's location, the inclination of the telescope, and yes, we just want to devise an observing setup, trying to mitigate these issues like overall. We need to provide a wavelength uncertainty measurement as a complement to what we did so far. A goodness of fit and confidence in our estimation needs to be adapted from the CDF, fits described earlier as a part of the automation of our work. In practical observations, our single atmospheric absorption line, although it's strong, might not be inside the spectral domain of the slit itself, of the slit of observations, or it might not be observable due to atmospheric conditions. So we would want a set of multiple candidates instead of how I just chose to pick one line, depending on the emission and absorption properties. So the atmospheric would then be calculated as an average in the shift of all the lines that show the features. So in conclusion, we made the CDF analysis on CLE, on coronal emission lines, to recover physical parameters from them. And we used it to measure the confidence in the measured point or pixel provided. And finally, we used the atlas of atmospheric and telluric observation to select suitable line candidates to provide a wavelength calibration product, and tested this product on available spectral observations. And lastly, based on constraints, this work is planned, or yes, it's planned to be included in part or entirely to the level 2 coronal pipeline, which my mentors, Alan, Phil, and Kevin are working on developing at the National Solar Observatory. And that's it.
All right. Thank you very much. Are there questions from the audience? I do have a question. So in an earlier slide, you showed the ratio of the noise spectrum with the pure spectrum, and so if I think I may have missed slightly what the noise spectrum was, because I was surprised that for I, which is like the intensity, right, that you had a ratio of 2. Does that mean that the noise is twice as big as the signal?
Yes. Or that the noise would portray it being like bigger than it actually is.
And this is of a simulated data set, or?
Yes, it was entirely simulated since we don't have observations yet.
Okay, so you created a data set with a lot of noise, right?
Yes, yes.
And just to investigate, taking a, I'm just trying to understand why you're using such a noisy spectrum. Is it to really push the limits, or I don't know? Can you just expand upon that?
So I actually didn't add the noise. It was done by just this idea, the code made at HAO and NCAR, and It applied the thermal parameters and different velocities that I'm assuming would be mirrored in the DKIST observation we would get. I don't really know the specifics to that, but it would be pretty high noise, I'm guessing.
This is Ellen here. I can add another one sentence to it. The point of that simulation was to try to mimic an observation that everyone would want with DKIST, as in 5-second integration times for one slit position. And that's something you would get if you integrate through the DKIST telescope for just 5 seconds.
So 5 seconds is too short, right?
Yes, that was the point there. But but we used those observations here to show how you look at Stokes V, and for example, you see much more signal in it, especially if you're using integrated spectra. But then that's misleading because there's just noise there. The signal is completely lost in it. And that's what Atya tried to point out with that.
Okay. All right. That makes good sense. All right. Any other questions from the audience or from YouTube? All right. YouTube is silent. All right. Great. Good job. Thank you.
Right. Thank you, Atya. And please remember to give some feedbacks if you have time. Okay, our last presenter is Jeffrey Delaney from Central New Mexico Community College. Jeffrey, are you ready to present?
Yeah.
Okay.
My name is Jeffrey Delaney. I'm a student at Central New Mexico Community College. And over the summer, I did a project on the analysis of atmospheric seeing measurements. What we're looking at here to the left are the 6 GONG sites. GONG has been active since 1995, and it was originally designed for helioseismology. And over time, it became relevant for space weather modeling. GONG stands for Global Oscillation Network Group. GONG sites are distributed around the globe so we can observe the sun 24 hours a day. Mauna Loa is in Hawaii, Big Bear is in California, Uniper is in India, Learmonth is in Australia, Sierra Tolo is in Chile, and Tahiti is in the Canary Islands, Spain. So atmospheric seeing. Atmospheric seeing refers to the blurring and steadiness of the image of astronomical objects caused by the Earth's atmospheric turbulence when observed through a telescope. Atmospheric seeing quality affects almost all ground-based astronomy, from choice of site to telescope design to interpretation of data. The goal of my project is to rank the 6 GONG sites in terms of the seeing quality. The image to the right is included. The image to the right displays the perturbed wavefronts that get broken up by the turbulent layer. If you're looking at something from a far distance, the turbulent layer will perturb wavefronts, causing the image and seeing to blur. Plane waves from a distant point source can appear to be clear if there's no turbulent layer in the atmosphere, which is unlikely. Data analysis. So relevant data used in the project are H-alpha images in a 2K by 2K image size at a 1-minute cadence and a 1 arc-second pixel size, acquired at 6 GONG sites from 2011 to 2020. H-alpha and seeing monitor data was taken simultaneously in Tucson, Arizona between October 22nd, 2013 to February 10th, 2014. Data processing. 3 parameters that pertain to seeing quality are extracted from the header of H-alpha FITS files: RMS, SkyBright, and sharpness. Correlation between sharpness and seeing measurements is used to scale the sharpness parameter in arc-second seeing data. I use a statistical analysis of proxy seeing data and their distributions. Sharpness, RMS, and SkyBright. So these are the 3 parameters I use when observing the data. Sharpness is the center disk of a 128 by 128 pixel extracted. These pixels form a region of interest, ROI, And that's used with the boxcar filter 9x9 kernel and is run over the ROI to create a blurred version of the original data. The original data is divided by the blurred data. The sharpness and the standard deviation of the ratio data is computed in step 3. Sharpness ranges in values from 0 being very bad to 1 being very good. RMS is using the above region of interest. It computes the root mean square of the original data. SkyBright is using the 320 by 320 pixels in each corner of the image. It computes the average. The image of the sun below was taken with a gong instrument at Big Bear. Looking at the wavelengths of H alpha 65, 62.8, the H alpha wavelength would be slightly reddish. We are looking at suspended material above the sun. Filaments are on the disk and prominence is above the disk, and they appear to be white due to the darkness of space. This will be a filament, and these are the prominences on the side. Looking at the center region of interest, this is a 128 by 128 pixel. The image processing technique is a 9x9 kernel, and the boxcar filtering takes an average of the 9x9 images and smooths it out. Matter is being lifted by the sun's magnetic field. H alpha images from Mauna Loa on the left and Big Bear on the right. Atmospheric seeing has smeared features in both images, but less so for Big Bear. This is reflected in the higher sharpness value for Big Bear, 0.01588 versus 0.01224 for the Mauna Loa data. Higher values indicate better seeing. This is the effect of different seeing. The dark line is a filament and the brighter blob is a plage with 2 sunspots. So this is going to be the filament, this is going to be the plage, and you can barely see the 2 sunspots in Mauna Loa, but you can kind of see it in Big Bear. The plage is a region of intermediate high magnetic field ranging from 10 to 200 Gauss, and the sunspots have 10 times higher than magnetic field. Mauna Loa is a lot more blurred when you're comparing it to Big Bear. Looking at the features of Big Bear, it's a much sharper image. You can see the RMS for both images is nearly identical, so it's going to be down here at the bottom. And the SkyBright indicates Mauna Loa is better, so this is why we chose to focus on the sharpness parameter, just because the 2 other parameters were not as clear. Converting sharpness to arc seconds. A linear regression was computed using the data between 2 vertical dotted lines between 50 and 100 1/over sharpness. The correlation coefficient is relatively high at 0.95. Scaling parameters were applied to all sharpness data, not just within 50 to 100. -1 to 1 is the scale used for computing correlation coefficients. It can indicate that all data follows a linear line well. 1/over sharpness high values means it has bad seeing. Outside the linear region, the instrument behaves differently because the values are not accurate. So that's outside of the 50 to 100 range. So this is an example of daily seeing for Big Bear and Mauna Loa, showing all this data for a full month of observations. Plots were chosen to show typical behavior for these sites. Some days were excluded as their trends were atypical. Big Bear seeing improves throughout the day, and Mauna Loa seeing degrades throughout the day. Big Bear starts out bad in the morning, but slowly gets better throughout the day. Towards the end of the day, the plots become more scattered. Mauna Loa has incredible seeing for a little bit in the morning, but isn't enough to consider the site as the best. Later in the day, the points become more scattered, destroying this quality of seeing. I found data gaps at the -5 hour angle, and they occur for every site in the early mid-morning. So that would be these data gaps right here, and they occur for each site. The average and standard deviation is shown with the blue dots and bars. The error bars are much smaller for Big Bear and much larger for Mauna Loa, showing the negative effects of turbulence. This is another example of daily seeing for Sierra Tolo and Utica, showing full months of data observations. The plots were shown to show typical behavior for these sites. Sierra Tolo is similar to Mauna Loa, where it has good seeing for a brief period in the morning, and Utica is consistent with not good seeing. just due to the arc seconds being so high. Note the sparsity of the data due to the approaching monsoon season in Untitled. This is another example of data seeing for Tahiti and Lear month, showing all data for the full month of observations. These plots were shown to show typical behavior for the sites. Tahiti is similar to Mauna Loa with the good seeing in the brief period in the morning, and Lear month is located near the ocean, and it has good seeing in the morning and late afternoon, but during the day it's not so great. And the error bars are just as not as big, or the error bars are pretty big. This is the overall seeing for all 6 gong sites for a 10-year period. This is what I mainly use to rank the 6 sites. The overall seeing quality of all 6 gong sites is relatively good, with plots ranging from 0 arc seconds to 4 arc seconds and a relative frequency of 0 to 1. Looking at the total observations, Big Bear is the best from 1 to 2 arc seconds. Majority of Big Bear data falls between 2 to 3 arc seconds, but it has the highest range from 1 to 2 arc seconds compared to the rest. Sierra Tolo is second best, and once again, the majority of data falls between 2 to 3 arc seconds, like Big Bear, but it has the second highest range from 1 to 2 arc seconds. The remaining sites are similar but don't look as good, as they appear to have issues that affect seeing quality. Every single data point was used in these plots. Seasonal variation for the 6 sites over a 10-year period. When you're looking at Big Bear, you can see that January compared to August is a lot different. So that's going to be because of the winter, you're going to get bad seeing in the winter and then better seeing through the summer. There's a seasonal variation for all sites. Untitled has problems during monsoon in August, as there are barely any data points collected. Monsoon affects the duty cycle in Untitled, which is about 47%, and Lear month has the highest duty cycle at 70%. The duty cycle is all the data that was collected versus all the data that could have been collected. It is approximate because we assume the 12-hour day to compute the data that could have been collected. Biannual variation of seeing quality for 2 sites. Notice the considerable changes at Big Bear over time. From 1 to 2 arc seconds is very good from 2011 to 2016 even, but from 2017 to 2020, it drops substantially. This shows how data changes over the years. Even though we included all the data points, there are changes that occur. Further research is needed to understand and possibly not use some of the data from some of the sites because we have noticed an interesting variation. This is another biannual variation of the seeing quality for another 2 sites. Considerable changes at Tahiti over the years. Take note of how Tahiti changes over time. It was decent seeing from 2011 to 2016, but from 2017 to 2020, there's a slight shift in data with the majority of points moving to 3 to 4 arc seconds. It's like a substantial amount of points moving from 3 to 4 arc seconds. There were instrumental issues with Tahiti, and there were camera issues where there was oil spilled on the camera. So in conclusion, I have the preliminary rankings for each site. Big Bear is the best at the #1 spot. Sierra Tolo is second, Lear month is third, Mauna Loa fourth, and Tahiti fifth. And then Untitled comes in dead last because of the seeing over time. That's all.
All right, very nice, thanks. Are there questions? All right, well, while those questions are appearing, I do have a question. So in the plots of seeing versus hour angle, can you describe what hour angle means?
Hour angle is like the universal time, but it's like taken at different angles, different like hours of the day. So like where the sun sits.
So at hour angle 0, does that mean the sun is directly overhead?
Yeah.
Okay. So this gap at -5 is pretty curious. Why is there a gap at -5 hours everywhere?
I think it was an instrumental issue. I'm honestly not too sure. I noticed that whenever I was doing all the graphs for each site. And Alice and I we went through the FITS file and we found that there was like no data at all during that time for each of the sites.
The for Learmouth though, it's like at -4 instead of -5.
Yeah, it's like it changes a little bit, but it's pretty consistent in the sense of I think it was from when we downloaded the files, the H-alpha files.
It's just I'm just trying to visualize. I mean, is it something where they do some sort of calibration at that time every day, or that the file is being transferred or something? I don't know.
Jack Harvey has Harvey has put in the chat that the gap is due to calibration sequences.
Yeah, I was about to say that. It is a calibration, daily calibration.
Okay. All right. That's just when they do the calibration every morning. Okay.
It's always an explanation.
Are there other questions?
So I have another question.
Yes.
Nice talk, Jeffrey. If you could go forward a few slides to the seasonal variation. So there's a lot of information on here. I was wondering if you could sort of talk us through this again. So high number of arc seconds is better seeing, is that right? So we want to see any of these that are skewed towards larger numbers?
No, you want to see them that are skewed towards lower numbers. So
lower numbers, okay.
Is going to be your best seeing.
I see, okay. And so then lower numbers, and then also just seeing the variation throughout the year. I see, okay. That's where I was getting mixed up, was I was going from sharpness to 1/over sharpness to arc seconds. That progression I didn't keep up with.
Yeah, so
can you, I was going to, go ahead.
No, you go ahead.
No, I was going to ask you to explain sharpness, but I think that was what you were about to do.
Yeah, so sharpness is going to be like the higher the number, the better the seeing. But when you do 1/over sharpness, it does it inverse. So you do the lower the number, the better the seeing. And then when you change it to arc seconds, it's going to be the lower the number, the better the seeing.
Okay, and the change from sharpness to arc seconds, that was that correlation graph that you had earlier on, is that correct?
Yeah.
Okay. This one, okay. So low seeing, oh yes, because you can see smaller details. All right, I'm with you. Thank you very much.
Yeah, of course.
Any other questions?
I have a comment. So if I want to understand, you have used the correlation between the sharpness and the results that you have from the seeing monitor, right? And you have the seeing monitor measurements only from one site. Is this correct?
Or what was that again? One more time?
So your estimates are based on the correlation that you made between your sharpness measurements and the results that you got from the seeing monitor.
Yeah.
And you have only measurements from one side for the seeing monitor.
The seeing monitor, yeah. Luca pulled the data from Tucson.
So the thing that according to my experience, you have to be careful when you look at these sharpness proxies for seeing, because especially in these type of measurements for these observations, there are two things that determine your sharpness. The first one is the seeing, and the second one is the scattered light. So I would be just a little bit careful in calling that seeing. That's my comment, but I don't know if Jack or Alice or Luca have any comment.
Yeah, I have a comment on that. So in this particular plot, seeings are actually real seeing measurements.
Yes.
Okay, so 1/over sharpness is whatever parameter you derive from H-alpha measurement. It's true that actual correlation between those two quantities is a little bit tricky. There is a lot of things going on, and so it's not exactly perfect, I would say. Okay, so this is basically some sort of a rough estimate, because we don't have, unfortunately, seeing measurement taken at all time at the 6 sites. So this is kind of trying to reconstruct to some degree, in average, I would say, the seeing history at those 6 sites. So even the numbers for the inverse of the sharpness that you get after the conversion are probably not extremely accurate. You know, when you go to the next plot, if you go there, Jeffrey. Yeah, so you see those numbers. So, I mean, there is some uncertainty that comes from the actual cross calibration between those type of measurements. So, I mean, it's a long story, but even, you know, when you take a seeing measurement with a proper instrument, you don't really measure arc second. You still also need to do a calibration into arc second. So those numbers are basically indicative of the thing. They are not to be taken, you know, in terms of absolute value.
No, yeah, I understand. I mean, anyhow, like if the idea is to compare the different sites, definitely that looks like, you know, this is a good metric to.
Yeah, and that's why we basically average a lot of those data points together, because at least, you know, we can probably trust those averages a little bit better than individual single measurements.
Mm-hmm.
So they should give at least a reasonable overall behavior for the different sites.
Yeah. Yeah, no, it's very nice, and I found it interesting, and I was surprised by Manolo. I thought would have been one of the best. Okay, thanks. Nice job. Thanks.
Thank you.
Are there any questions from YouTube?
No, not at this time.
Okay. All right. Well, if there are no other questions, then let's thank Jeffrey again. Nice talk.
Thank you. Thank you.
All right. I think that that wraps up for today. Hopefully, I'm not forgetting anyone. Please fill out evaluations when you get a chance, and we'll work on compiling those and get them out to you as soon as possible. Otherwise, the next event will be tomorrow, the poster session. So we would like the students to show up at 9 a.m. Mountain Time in order to do all the logistics of setting it up and any end of program talk that there is. And then starting at 10 o'clock until noon Mountain Time, the poster session will be active, and we invite people to join the Zoom. And we believe that we have a system that works where you can each student will be I see Claire crossing her fingers. Each student will be in their own little poster alcove, their own little breakout room, and you will be able to move from room to room to talk to the students individually. So yep, we'll see if this works, or we will either be